Hey Quartz, you should be able to hear me. Yep. All right. Give me a second here. I'm still setting things up, and then we'll get ready to go. Give people a few minutes to show up. All right. Grab a couple water bottles, ready to go. Why does this stupid thing on YouTube always pop over to the left? That's so dumb. Hey, how's it going, Truck Pam over on YouTube? I don't know why this fucking thing. All right. All right. All right. I'm good. So, let's see if we can't hop over to our streaming default. There you go. We are going to look at. We'll do a little bit more of the network primer from the other night. We'll kind of run through it again and keep going further. Maybe we'll even finish it tonight. Who knows? And then, so it'll be a little bit of a refresher on it for people that missed it the other day. Won't go as deep as we did, and then we'll go into the new stuff. So, if anybody wants to follow along with that, we'll do that. And then also, I'm going to build a lab. I have a lab kind of in mind. If I don't get through with that tonight, I'll do it tomorrow. It's not a big deal. But so this is the Prolog networking primer. Again, if you guys were here the other day, we had a couple of XKCD to get your thoughts on networking. And then we started talking about, here's our topics. How does communication work? A little bit of a networking overview, and then we'll deep dive into each of the different areas. That's kind of how I like to show you guys networking. That's this is kind of like what I show my college students. My college students tend to get much more of a structured, walk through everything, but this is a high level of just things that I've been teaching and doing forever in the networking world. So we'll touch all these pieces. So what you should know at the end of this: describe basic components of computer networking, understand how we subnet larger networks and smaller ones, and understand how the data flow. Out of scope, you won't become an expert watching this, right? We talked a little bit about there's a simple communication model. There's these 5 pieces that have to be there. And if these 5 pieces are there, communication occurs. If any one of the 5 pieces is missing, communication does not occur. That is true generally across the board for all systems. You got a sender, a receiver, a message, a medium, and noise. You always have those 5 things. Never less for a communication to occur. Never. All right. So here's some networking fundamentals. We went over this the other day, but there's a sender, a receiver. There is data circuit equipment and data terminal equipment, and those deal with who is sending the data and who's receiving it across the line anywhere in our system. What kind of equipment is on the ISP side, which is providing typically the clock rate for us of serial lines and telling us how fast our data can flow and that kind of stuff. DTE are underneath the DCE as far as they are. We don't use the term master and slave anymore much, but they are the workers underneath it, if you want to think of it like that. And it's typically your side of the connection. Then we have this concept of an autonomous system. That's what I control. Anything in my control is, or one administrator is considered an autonomous system. And the demarcation is where I touch any other system and allow data to flow between me and them. And then a metric is any unit of measurement we use to differentiate systems. Like I have my metrics are maybe I'm looking at the fact that it's a 1 gig, a 10 gig, and a 100 gig link, and then I can choose between those based on that measurement. but I can't look at one of them as 1 gig and another one as fiber and be like, those are the same, because they're not the same metric. You're not using the same type of thing to compare between them. All right. Talked about the 3 primary types of addresses. There's layer 7, which is DNS addressing, layer 3, which is your IP addressing, and IP addressing comes in either your IPv4 or your IPv6 flavors. There's a layer 4 type of addressing called ports, but that doesn't really fit into this, so we'll talk about that as we get to it. And then there's layer 2 MAC addressing, which tends to be how your system sees other systems in its directly connected network, right? The hardware addresses for Mac are 48 bits long. The first 24 bits are the vendor portion, and the second 24 bits are the host portion, right? So there's that, and you can tell exactly what something is based on either the first 24 or the last 24. Now these are represented in hex, so each of these is 4 bits. So that's 4 bits, that's 4 bits, that's 4, that's 4, that's 4, and that's 4. So that adds up to 24 total, and then 24 total over here. That's where you get the vendor portion and the host portion of those. All right. So we won't go too far into that. I mean, I can show you that, you know, if you have some device you want to look up, you can actually, there's places you can go and you can say like MAC address lookup, right? And then you can say, hey, I've got this MAC address on my network and I want to see who it belongs to. So, you know, maybe I pull up one of my home machines here and I do an ARP-A and maybe I don't have ARP on there, right? And then I go to ARP and I go, okay, well, let's take one of these machines, like maybe this one. This one would be a fun one because I know what this type of device is. But I come in here and I drop this in and I say, well, what type of device is that? And this thing will probably tell me what type of device it is. It comes from Asus Tech. And these are kind of things that you might not want to show somebody, right? It gives you information about the type of device it is. And then it tells you a little bit about who made it and all that kind of stuff. Hey, Robodom, how's it going? We're just going over networking a little bit again. We're showing some things, and I'm showing how you can determine, and it determined all that from the first half of this, so you guys know. It even says it right there. And it gives some information about it. So, all right. So those things exist out there in the world, and you can go play with them if you want to. All right. So then we did a quick binary rundown. Some of you guys might remember this. I'm not going to spend too much time on this like I did the other day. I really broke this down on the other stream, but if this is interesting to you, go spend some time with it. But basically you've got some address over here, 192.168 and maybe 200.1 or something, and it's a /26, and you're like, well, what the heck is that, right? Like what are we looking here? And then we figure out that we can break these down from the decimal numbers that they are down into binary, and we looked at all that stuff, right? I'm not going to rehash that too much because that'll take some time, and I want to get further along in the talk so that I can finish it. But if suffice it to say, if that's interesting you, go spend some time with our talk from Monday. What was Monday? The 19th, right? Go look at the 19th, and that's where we have it. Hey, Natasha, over on the YouTube side, hopefully this stuff is useful to you. I'm not going to break this all down right now, but I will show you guys again, why do we subnet, right? We're given some big network, 192.168.1.0 in this case, /24, and there's 256 total addresses in one giant space. Now, you can only use 254 of them. We always throw away 2, and if you want to know why we throw away the 2, it's because the first one, which is all zeros in the host address, is the network name or the network ID. And the last one, which is all ones in the host address, in the host portion, is the broadcast address, or bcast as we sometimes call it. So we take this, and this is one big network, so why do we subnet? Well, we want to chop that network up. I want to take one bit and say, okay, I'll take that first bit off of this. Instead of being 00000, the very first bit will be network for me, and it will be a subnet. And it will either be a 0 or 128 if I have it off or on in that first far left bit place, right? And yeah, Chico saying, keep up the great work, Scott. Yeah, hopefully this stuff's useful to you guys. He's over on the YouTube side. trying to keep this stuff useful for you guys. But anyway, so here, those are our two networks now, and then here's our two broadcasts. And somebody that was broadcasting in here would only broadcast all these addresses, and somebody over here would only broadcast to these ones. And that's what we call broadcast domains, right? Now, we used to have collision domains and broadcast domains. We still have, well, you still have collision domains if you have hubs. If you have a switch, though, you never actually have a collision domain anymore. And I actually dislike when I see questions like that and people are like, well, you still have a collision domain within that. Well, it's like, no, if you have full duplex communication, my send is to your receive, my TX is to your RX, and your RX is to, and your TX is to my RX. So there is no collision domains anymore with switches. Switches completely negate all of the concepts of collision domains that we used to have. In fact, that's one of the reasons Ethernet is so widely adopted, is because in a zero collision environment, Ethernet 2 just runs super fast. We'll talk about that when we get down to layer 2. But let's keep going through this. Again, we're not spending too much time on this. We keep chopping these up. We keep getting smaller and smaller networks. And then we keep chopping it up to, like, even in this case, we've borrowed 3 bits now. And those 3 bits have the effect of giving us these networks that are separated. And then when we were doing the last little class, if you want to think of it like this, I chopped these up and I proved to you that these are all the addresses you get mathematically, right? We're not going to spend a lot of time on it, but that's this part here. So I just wanted to hit that primer real quick before we move forward, okay? We talked a little bit about the OSI model. Why do we like to model things as engineers? Some of you guys that came to my engineering talk on the 3rd and the 4th, when we were talking with the ProLug group, which is our professional Linux users group, I talked about engineers build engines. We build things that cycle, right? And engineers in the networking space build things that send, but at the end of the day, they're still cycling through an engine of some model. This model cycles through. We start at the application layer, data flow down from application to presentation, presentation to session, session to transport, and communication occurs between each of the layers as they interface up and below. So the thing that we need to do here, there's 2 reasons for models. There's 2 reasons for models. They are used to teach, right? I can teach you based on these models, and we can just sit around and talk about these. And when you say, well, Scott, what are you talking about? And I say, well, I'm down in the physical layer, and we're talking about this part. And you say, okay, so I'm not worried about the other part. And I'm like, no, this is all just cloud right now to you. You don't worry about this stuff right now. We're down here at this layer, right? Talking about this, and we break this out and have whole classes and whole, quarters on this kind of stuff in the college level, right? And this is what network engineers do. And then the other way is for like what we would call like interoperability. Or what you might think of as modularity. So modularity is this. If we were going to change out, like at your house, right? If we were at your house and we said, hey, you know what, we gotta take we gotta trade out, we gotta put in a new switch, right? So switch like a router. You got a little router sitting at home like this, right? And routers, we tend to draw routers more like this, right? And then switches we draw more typically like this, right? That's typically how we draw these things. So router is normally denoted as round in layer 3, and then a switch is down here at layer 2. But just for now, don't worry about the roundness or the squareness of the thing. Let's say you had to get rid of your router and put a new one in. And then I told you, well, when you do that, you've got to throw away all your cables that are going everywhere. Got to throw away all your cables. You got to go throw away your NIC and put a new NIC in your computer, because none of that stuff works. You would be like, well, that's stupid as crap. I just want interoperability. I want to be able to pull one out, throw it away, and put another one in and not change anything, even with an upgrade. So what happens with this interoperability and modularity is, let's say we have some great addition up here at the presentation layer. Presentation does encoding. We're going to get to this in a little bit. Encoding, it does encryption. And it does one other thing, it does compression. typically, right? These are the things that happen at at presentation layer. Well, what if we come out with a cool new encoding and compression scheme, and it's like 50% more efficient? But then I tell you to do that, you have to rip all this stuff out and redo all your cabling and everything. You'd be like, that's effing stupid. Why the heck would I do that? That's dumb. Well, no, with a good model, when you have a model and things communicate up and down like they should, only with the components they need to, you can basically take this out and put a whole new one in without affecting the ones above it and below it. The example I always give people is if you've ever seen if you ever built with Legos, right? And then you've got these little Legos put together, and they're a little brick wall of Legos, right? And they're kind of a little firewall looking thing, but they're a little wall of Legos, right? And you want to switch this one right out here. You have a bunch of greens, and you want to take this line out and put yellow ones in there. Well, that should be really easy to do. Just unsnap them, pull them apart, and put the yellow ones in, and then slap them back down. And that's exactly how a model like this works, right? So as we get to each of these pieces, remember that we teach with it so we can break down each individual piece, but then it's also super useful for interoperability and modularity, because components only talk to the layers above and below them, and they only talk across to the other side. So again, as data are flowing down, application is talking to presentation, presentation is talking to session, session is talking to transport. This is coming down, but logically data at the transport layer is only talking over to the transport layer on the other side, logically, right? At this layer, at this header, you've got a port number, right? You've got a source port and a destination port. You'll see them often written like this: S port and D port. Like if you do filters inside of Linux, you'll see S port and D port. Source port and destination port. Well, if over here, if this is a web server, right? The system at the transport layer, it's probably listening on port 80. Maybe 443 if it's like TLS or something. But then when my destination port, as I send data over there in the header, is going to be port 80 as the data are flowing. But the only system over here that's aware of that is the transport layer. That's the only layer that's aware of what's going on inside of this header. Nothing else in here cares about the header. Nothing else in here inspects the header of the transport layer as it goes down. Now, as I say that, your side right here, your network layer, is aware, again, as the data are flowing down, your network layer is aware of what's flowing down to it. And it does sometimes put that in the header. It tells you what the port is of the session above it, and or what of the segment above it. And there's a reason for that, which we should be able to get to when we get to that section. So, plus I got to think about it because I got to remember what it is. Got to remember what that is. All right. So, data are flowing around. We've got it all set up. And we're going to break down each of these different pieces. That's kind of the next part. This is where we had gotten to on Monday night. And then I kind of stopped when we got to here because it was just going to, I was just going to start kind of, I think I was petering out and losing steam and stuff. So I have a little more energy tonight. We'll go. I did work literally all day, and I've got a little bit more work to do tomorrow. But hopefully I got a good weekend here where I'm not doing too much work. So we'll see how that goes. All right, so this is the OSI model, right? I drew this out, and this is from other systems that I've worked on over the years and stuff, and we can see all these things happen. In fact, let me stop myself real quick and tell you guys, one of the things you should do if you're watching this or doing this stuff in general is you should go download yourself a version of Wireshark. It's free. You can go grab a version of it and have it for capturing stuff, and it will help you to understand a lot of these concepts as we get to these different parts, because I'm going to be using it here. Okay, so let's go. At layer 7, application data layer. What's happening up here? We've got all of this, again, we know that we've got that highest layer of addresses. We've got this highest layer of addressing going on called DNS. DNS is mapping well-known names like www.google.com to some IP address for our system to use. So what else is going on at layer 7? There's HTTP, HTTPS, DNS. There's all kinds of other protocols that are moving data around your network. This is just some of them. This is probably the ones you interact with the most, right? Hitting a web page and then DNS, right? But we can see some of that, like we can see that DNS happen, right? We can go to a Linux box. Whoops, notes. We can go to a Linux box like this, and we could just say let's just, there's a few tools you have, right? NSLookup, www.google.com will give you a little bit of information about, okay, so I went out to figure out who Google was, and I went to this internal server in my home lab, and it gave me some information about maybe where I can find Google via an IPv4 and an IPv6 address. And I say, okay, that's cool, NSLookup, do that. What about, we've got a few other commands that'll do kind of the same thing. We can dig Google, and typically dig, look, it'll show you that I'm on some type of Red Hat box, or I'm using dig from Red Hat, right, some tool. And then I went out and I found that Google has an A record, right? A records are your IPv4 addresses, mapping of IPv4 addresses to the name. If there's a quad A record, which is 4 A's, AAAA, that would be an IPv6 address. And I think I can flag dig to give me IPv6. So let's man dig, because I don't do it as much, and look for IPv6, right? And then it says, yeah, 6. So I should be able to use like a -6 here. And it should give me that same answer, I think. It might just use IPv6, so that I may have just not be get out, but that may not have given me what I wanted. Yep. So that didn't work. Let's go read our man again. Let's see if we can get IPv6. -I, maybe. -X. I don't see anything in there that'll explicitly do it. But let's do our we did our NSLookup. We did our dig. Let's try one other one that I like, host. And host did find an IPv4 and an IPv6 address of the system, right? So for Google, it gave me an IPv4 and an IPv6, and that IPv4 is mapping as we kind of expect it to here, right? So the system was doing all of this stuff, and we can do well, if we wanted to, we could do a TCP dump and track the data and the requests that we're doing here, right? If we really wanted to. But the point is, we have these tools, and you want to know how to use these tools, because here's the thing, like I tell you guys, if you just ping something and it works, well, good, go on your happy merry way, everything works. But if it breaks, now we need to go dig into why. And one of the things about it is, if you can ping something via name, that you've resolved all the way through layer 7, all the way to a DNS query. You've gotten to a DNS server somewhere, or it's local. But if it's a locally resolved address, you can tell that by using dig. It'll tell you, right? There's a bunch of common devices that kind of exist up here at layer 7. Like, and again, we're talking networking devices, so I'm not going heavily into like on the system type devices. This was supposed to be like a networking primer. But the types of devices here are web application firewalls, reverse proxies, which are what we call load balancers often, and then there's next-gen firewalls. We used to have, back in the day, and they do kind of all layers of things, but we have a thing called a Packet Internetworking Exchange, or a PIX style firewall. That's an old name from Cisco. And then they've moved over to the ASA style firewalls, right, which is the adaptive security algorithm. But The point is, these and those devices tend to operate down at layer 3, but networking devices can do all kinds of things. So let's look at what these ones are focusing on here. So a proxy server, if you ever hit a proxy of any type, and VPNs are forward proxies typically, which is proxy up here. This is just a regular proxy, but another way people will think of this as a forward proxy. So you want to go to, proxy to Europe or something. You're in the US and you want to proxy over to a server in Europe, and you do that over like a VPN or something. And proxy literally means on behalf of, and then you get to hop onto, like, I don't know, Netflix, and then Netflix has some version of a show that you can't watch from your home address or something. And I've heard of people doing that. I don't do that because I don't guess I care about shows that much, but that's what a forward proxy is, or what most people just think of as a regular proxy. You will find a lot of proxy servers acting, so this type of process and this type of thing will sometimes be built into desktops and stuff. Hey, how's it going, Rossberger? I was on earlier when you got off. I was trying to get you to start your whole stream over for me right at the end of the day. So that's kind of one of my favorite things. I'll jump into Rossberger's stream. It doesn't matter what time of day or what he's doing. I'll try to get him to start over. So, but yeah, so a forward proxy is what a lot of you guys are used to. This is, you're going to a system, and then it's acting on behalf of you and sending you out to the internet. Commonly known ones of these that people use are Tor, Tor, which is the Onion router, but the Onion router has been compromised for like 10 years now, so I really wouldn't use that. It's no real protection against cybercrime or doing any of that kind of stuff. I'd really just tell you, don't do ratchet shit on the internet if you don't want to go to prison. But anyway, so what's a reverse proxy? A reverse proxy is a completely different concept, guys. This is how we start to build into what we call high availability. Your clients come in and they hit one IP address. They hit one node on front of your Kubernetes cluster or something, right? And then from there, they get hit to all these different back-end application servers. And they don't see anything different. They're just a client coming in, maybe checking into Twitch or something, and then they're going to any one of these different back-end application servers. Well, the reason reverse proxies are so powerful is this. If I'm sitting here like this and I don't let you see how the biscuits are made back here, right? If I don't let you see how the servers are working, and I've got 50 application servers back here, and you guys are coming in, and then I want to do work on my servers, I can roll through them in batches, and I can work on like the first 20, and then the second 20, and the last 10. And you guys out here are none the wiser because I'm draining out connections via the back of my reverse. These are very, very advanced boxes nowadays. There's Nginx reverse proxies, which are pretty common inside of Kubernetes. There are Apache can be used as a reverse proxy. There's all kinds of things. But at the end of the day, the way I always explain this to people is and this I do this to get a visceral response out of people. But like, imagine I came to your house, right? I'm one of these clients. I come to your house and I'm like, hey, I've got this letter I'm going to give to your kid. I'll just go ahead and take it to their room. And you'd be like, oh no, you're not. You're going to stop right there. I'll take it to their room for you. If I even let it go back there, right? Which is another concept of reverse proxy. We can defend our internal resources, right? Yeah, so Robodom, this is how we do higher availability. When we start to look at high availability, we can roll through and work on... I can be working on one of the rooms and move the kids, as it were, in this case, somewhere else without people knowing. They use Google front end, which essentially super advanced reverse proxy for all their services. Yeah, IO Fault, that's awesome. I don't do much with Google. I'm much more of an AWS guy. But yeah, AWS load balancers do the same thing. And their reverse proxy, you can actually configure it to check, like, hey, check that the application servers are pinging. Check that the application servers are listening on port 80. Check that the application servers have a proper TLS validation endpoint. You can terminate. So one of the things a reverse proxy can do that's actually very, very useful is it can terminate TLS connections. So your clients connect here. And you guys have heard me say this before, but your TLS connection, the initial handshake that happens, and this is outside the scope of this. It's in one of our other talks. But when we get into how that handshake occurs and the client knows that you are who you say you are because of a certificate authority, a third party has introduced you, what will happen is we can terminate that process right here and do all the encryption here. What does that mean? That means that this back here, this back end, is free of all of that weight, if you want to think of it as weight, of encryption. It's unburdened by what has been. No, I'm just kidding. It's a political joke. But anyways, the point is the client can terminate the encryption process here, and this can be encrypted, and then all the way back here can be much faster, and you don't have to go TLS encryption all the way to the endpoints. All right, so those are what proxy servers do. I tell you guys all the time, if you're watching this, pull up a notepad, go like this, and say, "What the heck is a proxy or a reverse proxy?" Right? And if you didn't catch any of that, or you want to go look it up, now you got it in your notes to go read, because I guarantee you, watch this. I'm just going to go to the Googles. I'm going to go to the Googles right here, and I'm going to say AWS is what I like to do. Reverse proxy. What the heck's a reverse proxy? No, I want to read somebody's blog on it. Somebody give me a blog post on how a reverse proxy works. And here's somebody showing me how it works on this. And look, he's got a way of showing that it's doing all this other stuff, ngrok, whatever this tool is. And this is probably something that, look, Flask and ngrok. Some of you guys have set up Flask with me before and that kind of stuff. But look at all this stuff that you can do. Oh, I want to do a lightweight on-premise API connectivity type for inverting traffic proxy. And this guy from a few years back explains to you how this works. And then you go spend some time with it, right? And then you grok it, which just means to understand. So you take this and you write in your notes, right? All right. So layer 7 firewalls. What are layer 7 firewalls? If we're talking about the whole stack, the whole everything all the way up to the top. At layer 7, we've got Unified Threat Management, UTM. They are multiple levels of, or multiple layers of security. They operate at layer 7. They operate typically at layer 4 and 3. Some of them will do all the way down to layer 2, but remember layer 2 is really just the next hop. So we don't typically have to worry down at data link layer, but maybe for MaxSec or for some of your VLAN stuff, that might work. We've got these NGFWs, next generation firewalls. They're application level firewalls that are aware of what the application's doing. What I mean by that is they are aware of the headers that are being passed in to the system as your as a web request is coming through and that kind of stuff. They're looking for well-formed application requests. They're looking for multiple concurrent connections. Down at layer 3 and 4, at layer 4 specifically, they can look for what we call embryonic connections. Embryonic connections are half-open connections. So if you guys have never heard of this, there's an old attack. There's an old attack. It's one of my favorite attacks in all the world. So this is how we used to do a three-way handshake. So the three-way handshake looks like this. It's a SYN from you over to me. I send you back a SYN ACK, and then you send me an ACK. Right? So this is you. You're sending me a SYN. I send you a SYN ACK, and then you send an ACK. Well, what an embryonic connection is when the first two of these have been done. And what used to happen, if you guys have ever heard of a SYN ACK attack, it looks like this. They send a SYN, and then you send back a SYN ACK and assign some resources, and then they just sit over here, and then they send another SYN, and you send back a SYN ACK and put some more resources over here. It would be like if I kept calling Robodom up. I don't know if Rossberger's still around, but if I kept calling Rossberger up and saying, "Hey man, I'm coming for dinner tomorrow night," and he goes, "I'm sitting out a plate," and then I call him up again, and I'm like, I'm coming over for dinner tomorrow night," and I start doing silly voices, and he goes, "I'm setting out a plate," Next thing you know, he's got 30 plates on his table and nobody shows up because I never do that last connection. Now look, SYNAC attacks, man, this has been a solved problem for a long time, guys. The SYNAC attack, we solved it 15 plus years ago in the networking world. And the way we did it is by these devices right here, and Pix firewalls do it too. They look for half open, what we call half open, or we sometimes call them embryonic. And I'm not gonna get super political about that, but what's embryonic? It means something that's only partially formed, right? Right? That's what the term means. So an embryonic connection can be, I'm trying to set up and make you just use a bunch of your resources to denial of service your equipment. And your equipment's being stupid and holding that open. So we can have timeouts for how long a SYNAC can sit. The machine, the devices between can look for half open or embryonic connections where you're not finishing that connection, and then they stop you from making more connections. Servers are smart enough now that if you don't send that last ACK, they just drop it. They don't even care. They just go about their day. Yeah, that's exactly true, IOFault. In fact, they literally will eventually abort the connections, yes. But your device could still be sitting over here just spinning, waiting for the resources to free up. And that longer timeout was how a lot of the people got the SYNAC attack to work. So if you've ever heard about SYNAC attacks, that's what it is. So you come over here and you go, what the heck and heck? Right? Is this guy crazy? How's it going, Johnny, man? We're just talking through some networking stuff. And then there's web application firewalls, right? Web application firewalls, WAFs. They're typically applied by cloud providers or third party directly in front of web applications. The way they do that, and I'll show you a picture in the next slide. The way they do that is is by certificates. Nothing can come directly to them anymore. You have to talk to another device and then have a trusted connection over. So in a lot of ways, a web application firewall is that's not its purpose, but it's kind of acting like a reverse proxy. All right, they're aware of what's called the OWASP top 10. And if you tell me, hey, I want to get into security of any type, I want to be API security for a company, or I want to get into, I know Robodom does a lot of front end type stuff. You need to know what the OWASP top 10 are. And they have the OWASP top 10 API. So you come here, right? Just pop this up. What's the OWASP top 10? These are the most common things in 2021, and they keep releasing them every few years. What are the most common things that are problematic with people and their front-end web design? Broken access controls, cryptographic failures, injection, insecure design, security misconfigurations, right? So then you come over here to your notes, and you go, what are those, right? And then you start just coming in here and reading about them, and maybe go and find some blog or some, video that somebody has on them, and you start to learn, a little bit about what the OWASP top 10 is, right? And then now you start to figure out, okay, that's how a web application firewall works. Now, there's a lot about web application firewalls in AWS and in their documentation. You need to know this thing front and back, at least for its capabilities, if you want to go take your AWS security specialty. I know I have one of those, as does Fisherman, who's one of our guys. I think he might still be streaming over on another stream, but right, this is what we do here. So, all right, so this is the WAF example for AWS. So you got users and attackers and people trying to get in, and the web application firewall takes the initial request. So your DNS actually points to your web application firewall first. The only people that can talk to your CloudFront or your application load balancer have already come through the WAF, and the WAF talks to them via certificates. So this is all trusted certificate traffic here. There's always logs. the logs are always going out somewhere, and they're being tracked and they're being monitored for all these things, and then they're modifying themselves in real time and checking. But the crux of it is requests are coming in. Maybe you've got CloudFront in front of an S3 bucket sharing your static traffic, and then anything that's going to be dynamic or changing is going to go to an application load balancer. Maybe that hits your API gateway, and then that API gateway goes and hits AWS Lambda and does other stuff like that. But maybe if your requests, whatever's coming through doesn't look good, maybe it's coming over here and it's getting blocked out, right? There's all kinds of things that are happening as traffic's coming through a web application firewall. There are a bunch of rules that you can just apply. There's allowed and denied lists, like maybe you just have bad actors that you've identified and you want to allow or deny your own stuff. There's SQL injection. And I told a story the other day where I was in charge of the WAF. So some of you guys know I did some security time. And I was in charge of the WAF for a big company. And what happened was we would get API requests from a vendor. These were supposed to come through. And what the API did, and I can just tell you this generically. Hey, Fisherman, how's it going? Thanks for the raid. I was just talking about you a few minutes ago and saying how if anybody wants to get their AWS security specialty cert, both myself and Fisherman have that, and you need to know the web application firewall pretty well. But what I was saying is in this company, we had API requests, and there would be about 50. What would happen with this API request that would come in? There were about 50 bank names. Let's just say 50. I think there might have been between 50 and 150, but bank names. And then I'm just going to give you some generic ideas about some of those bank names. I'm not going to tell you the exact names, but there was something like this. There was like and then there was like, I don't know, select. Those are not real names of the banks, but these are real things that were in the name. So now, if any of you guys, have any of you guys here done anything from, I'm pretty sure most of you here have done some SQL in your time. How about this? Select, union, select. Do you guys think that those would probably trigger possible SQL injections, even if they were legitimate traffic from, like this was like a client, a customer of ours. Actually, I think we were technically a customer of theirs now that I think about it. But it doesn't matter. They were trying to send us data, and that data was getting blocked at our web application firewall because the names of the banks and the names of the credit unions look like SQL injection. Isn't that kind of funny? I think it's hilarious. Maybe everybody else doesn't think that's that funny, but that's pretty funny to me. So, all right. Maybe I'm just jaded. Yeah, Bobby Tables, yeah. Select First Union, Bank Union 1. So we actually had to whitelist them to come in to bypass that. And that was happening in, that wasn't in a AWS firewall, that was in an Akamai firewall. But that's fine. You don't have to worry about who that was and how that was affecting them. But that was something that I actually experienced and had to deal with, right? All right. So what happens at layer 6? I mentioned this earlier. If you're gonna encode something, right, then you have to decode it at the other side. That makes sense. And if you're gonna squish something down over here, you need to reinflate it or decompress it over here. And if you encrypt it over here, you need to, decrypt it on the other side. That should kind of make sense to you guys. These are the major things that happen at this layer. The things that exist here. JPG. GIFs. Right? That'll start a fight. These are the things that happen here. Right? These are the protocols that exist to do these things. A bunch of your H232, there's a bunch of protocols that happen here. Yeah, H232. There's a bunch of them that encode, decode, compress, decompress, encrypt, decrypt, right? So there's all these things kind of happening at this layer to do this. And remember, whatever happens at this layer talks directly to the other layer on the other side, as we talked about earlier. All right. So layer 6, I don't talk about much because, frankly, as networking engineers, we don't care about it much. Layer 5 does windowing and flow control. Layer 5 directly interacts with the transport layer to say how many of these segments can I take before I acknowledge. So how many before I acknowledge, and then you can send more. So with and by the way, these both only apply to TCP. UDP does not care about this at all. Like if we're talking UDP is just what we call YOLO. It just launches it, or what's the young one that everybody says? It just launches it. Just suffice to say that it just launches the data. Just doesn't even care about this. But for TCP, there is a certain amount of send and receive, a certain amount that you can send before there's an acknowledgement before you can send more. Or if there's not an acknowledgement, there's a retransmit. Those are the two things that can happen. We can acknowledge, or we can say, nope, I did not get them in order. I did not get them correctly. Retransmit them. And guess what? You got to retransmit them. You can't keep going. You got to retransmit them with TCP. So guess what? If you just had to guess, knowing that TCP has to wait for an acknowledgement before it sends more, and it has to wait for this window, and as you're going to see in a minute here, it's got a bigger header. Which one of those do you think takes more time and has more overhead? TCP or UDP? UDP is a very lightweight header, and it just launches shit as fast as it can, with complete disregard for whether or not it ever gets there. Other protocols care if it gets there, but UDP itself does not. Which one of those do you think is faster? And here's a fun thought exercise. What do you think we're using right now? For me to talk to you guys, or if we were in like a Discord where we were having a meeting and we were all talking in there together, do you think we're using TCP? TCP, right? Establishing, and there's traffic back and forth and acknowledgements and stuff? Or do you think it's just shotgunning over as fast as it can with UDP? How do you think most voice and data and all that stuff is doing that? What do you guys think? Definitely UDP. Yeah, Code Reader's right. It's definitely, this stuff's all UDP. If I pulled up my Wireshark, which, right, we got Wireshark right here, ready to go. If I just turned this on this interface and started watching, we would see a tremendous amount of UDP traffic. If I just watch it here, and then after a little while I stop it. What is it? Wait, hold on. What's our what's my interface? I should be on one of my local connections. I wonder if this thing keeps adding local connections. Hold on. Didn't capture nothing. Hold on a second here real quick. What's my home on my system here, right? What's my Wi-Fi, or what's my connection? I'm on a physical connection here, Ethernet 4. So I need to be on Ethernet 4. And then now as we talk, and now as I say things, we're going to get a massive amount of what's going on in here, right? And we'll see a whole bunch of UDP, because the UDP is the actual traffic of us talking here. So then I can stop it, and then we can actually use this here in a little bit as we start talking about each of the different layers, as we get down lower to what we really care about as networking engineers. Because again, the top 3 layers, not as important to us on the system side. Yeah, Natasha, you were right as well over on YouTube. Yep. All right. So down in layer 4, there's 2 major protocols that happen here. There's TCP and UDP. We have 65,536 total ports. Those numbers are 0 to 65,535, right? And they can be listened to in either TCP or UDP for each of those, so that doubles the amount of surface area for an attack. TCP is connection oriented. There's that three-way handshake I mentioned earlier, the SYN, the SYNAC, and the ACK. Then we pass all the data in sequential order, and then we break it down when we're done. UDP is connectionless. It doesn't do any of those things. It just launches data. Layer 4 is where TLS lives. So when we talk about transport layer security, it's happening here at layer 4. So in my system here, right, my little Linux box, I do all Linux, guys, right? Like, I'm a networking engineer by, you know, schooling and just being a network engineer, but I mostly work all the time in high performance compute and Linux system. I do 95% of my day is looking at a terminal like this, right? Unless I'm doing STIGs. And then when I'm doing STIGs, it's a whole bunch of that STIG monitor. I've shown you guys all that, the STIG viewer. So on our machine here, we can do an ss-nt ulp and then just look at, here's all the things that my system is listening to. And I can see, is it UDP? Are we doing UDP unconnected? Or are we doing TCP and waiting for an active connection? Then there's all these other things that we can start to figure out here. We can say, well, if we're on TCP and we're listening, what are we listening to? Or are we listening for anybody? So this is anybody right here. This is anybody on IPv4 right here. And that's my SSHD. So IPv4 addresses can connect to this on port 22. And then down here, IPv6, that's the wildcard for IPv6, port 22, is also being listened to by SSHD. Right? So we can come in here and we can look at that. We can also look for LSOF-I on port 22. And we can see what's going on with port 22 in my machine. What am I connecting out and jumping into other machines? Are other machines able to connect back here? What's kind of going on in the system, right? And where am I connected to, right? All that kind of stuff is there. But again, we can kind of see what's going on in a system and understand how our system is listening. And this is a huge part of hardening a device. Hardening a box to only accept connections from the things that we want to. Because if I don't, honestly, right? If I don't have an answer for every single one of these, why the hell is it open? If I don't know why every single thing there is working on some externally facing device, this server sits out in the world. If I don't know why every single thing there is open, that's a problem. And that's probably not something I want to leave open, right? So this is a thing to think about, right? As you get into systems engineering and network engineering, is, well, why expose? And this is a huge question in like the cloud too. Like, why expose port 22 and 3389? Why do that? Those are the two ports literally everybody's gonna scan. Port 22 everybody knows is SSH, and 3389 everybody knows that's RDP, right? Remote Desktop Protocol. Those are, if you just close those two doors, you basically have everything just, you know, everything turned off. Nobody can connect to your stuff. What, in my home lab? Hold on. Let me check here. Yeah. And then by the way, did you guys know you could do that even if you're just on a Windows box? Did you know just on a normal old Windows box? Yeah, this is a Windows machine, right? I can jump into this and I can just say SS. In this case, I'll do a netstat /AO. You can do -AO, it'll accept it as well. And if you do that, this will show you everything in your home lab that's connected to anything too. Anything that's listening or any of that kind of stuff. And the reason I love the I'll show you guys this here in a second. This is actually one of my things I used to use when I used to clean people's computers out when I was a younger engineer and I would go work in people's homes and fix stuff. I'm going to do a Control-Alt-Delete real quick. I don't do that often on stream because I don't want to break anything. But did you guys know that when you look at... Hold on a second here. Oh, I'm breaking everything. Hopefully everything doesn't crash everywhere. Did you guys know that when you look at processes... Hold on. I'm going to look in details. Yeah, did you know that in details here, you can actually look at the PID here. So you see this process ID? So I can see all these things that are running in my system, right? And there's a lot of stuff going on, right? But did you know that you could, over here, say, what the heck is this? 18564 is something, or whatever this core HTTPS is. It's got this 17372. I can come over here to this PID. What did I say? 17372. 17372. Whatever the heck this is. Actually, that's my OBS, right? That's my Streamlabs. This is... Yeah, thanks, man. Code Reader, that's the goal, right? The goal is to show you guys that you can do this stuff, and hopefully the real goal is to get people into doing this stuff professionally, right? Like, we're all hobbyists in the Linux world here, but we also want to go make good money at it. And you guys that have been around know that I've been doing Linux for, 20 plus years now, and I've been teaching it at the college level for 16 almost. It'll be 16 in December. That'll be 16 years of college teaching. Almost half a lifetime, guys. But anyways, you can see my Discord and my code and all this different stuff I'm running, right? You can even see that I'm running WinWord, right? I'm running Word, OneNote, all that stuff. But the goal here is to show you guys, look, and if I really, really wanted to kill whatever, if I was really certain that this was a problem right here, whatever this 17372 is, which is right here, I can map it back to the actual thing that's running on my system. Do you guys see that? So every single thing that's open has a mapping, in this case it's a process ID, to something else. And I tell you guys all the time, in the systems world, everything is chutes and ladders. And I know that sounds really silly. You're like, oh, it's that game, that like that board game where things move around. Yeah. Everything points to something. Nothing's running on your system. Nothing's running on your system that you can't go figure out what the heck it's doing, right? And look, guys, I'm a Linux guy, but like this is Windows stuff. Windows also shows the processes listening on ports directly under the Performance tab, Resource Monitor, Network. No need to map between the two. Nice, IO. I did not know that, right? Like I am not a Windows guy. I bet there's PowerShell commands too, but my point is, like, I learn things one way and then I kind of just only remember them the one way forever. But that's a good thing. IO Fault pointed out that Performance tab, Resource Monitor, Network, and then you can just map them. It'll do it for you. Okay. So layer 4 has this, again, TCP and UDP. And what do we need to know about this, right? If you say, Scott, I want to pull up the big boy pants and be a network engineer, I say, okay, good. And it doesn't have to be big boy, it could be big girl pants. But the point is, let's do it, right? Let's go look at what we need to know about these last 4 things, because this is it. This is the crux of it right here. There is a TCP header. And the TCP header has all of these pieces of it. So earlier when I said that you send a SYN, and then I send you back a SYN ACK, and then you send me back an ACK, those are actually flags that are turned on. They're individual bit flags that are turned on in those. Yeah, big gender neutral pants. I like I like it. SK gave the that's pretty good. SK, he gave the way that you could grab that. Hey, will you put that, SK? I don't know if this would be too much trouble for you, but could you put that down in like the bash system tricks or in the Discord? Do you mind? I don't know if you mind doing that, but all right, guys, this is the crux of it, right? We start to learn this and we read about this. This right here is an awesome little model, but we're gonna jump back real quick into our system here. So this is our Wireshark. You can download this for free. And I'm going to close all this other stuff down and say, I just want to look at my TCP, right? I'm going to pull my TCP over here like this. And let's see if these things all map. I've got a source port 1935. I've got a destination port 51515. That's going to be right here. Now, if we want to go look at it, those are actually held over here on the right, and the source port is in hex, so 078F. We could map that out. 07 would be 00000111, and then 8 would be 8 would be 1000, and then F would be 1111, right? So that's how we would map those out in decimal or in binary, right? But that source and then destination, and then the sequence number. Remember, I said there's sequence and acknowledgement numbers. Those are right here. Sequence numbers are really long. 30. That's 30. So these are 16 bits and 16 bits. So that's a 32-bit sequence and a 32-bit acknowledgement number. And you say, well, how big is that? Well, if you just go to your Google and say 2*32, you would see that 32 bits is about 4.3 billion total sequence numbers you could have, or acknowledgement numbers. It's the same number as we have IPv4 addresses, right? There's data offset if there's some reserved for testing and that kind of stuff. And then there's all the things that can be tagged for if it's a SYN, an ACK, and urgent. So let's go back and look real quick. What was this? What were the flags that were on? This was simply an acknowledgement. Do you guys see that? There was no urgent, there was no push, there was no reset, there was no SYN, there was no fin. There was only, and look, I really like how this tool shows it to you. There was just an acknowledgement sent. So I'm just looking at, I think we're just looking at this first right here, right? So we were looking at, oh shoot, we lost it. Doesn't matter. We just grab any one. It doesn't matter which one we grab, right? And then let's go back to. I don't want to filter these in any way. That's fine. I don't care. Let's just grab a TCP one right here, and we see that this one's also an acknowledgement. And then let's go on the one that we're on right here. Let's right click and let's say follow the TCP stream. So now we can see that TCP stream only. And as that communication occurred, we're down here, we should be able to walk through and see, okay, the first thing, there was a set and an ACK, right? Maybe we didn't get everything in the communication when we first came on. And then there was a fin and an ACK. And then there was an ACK. And there was another ACK. Another ACK. Oh, I don't have these. Oh, shoot. These are not. They need to be in time order, guys. Yeah. And then you can go and you can see what was happening in this one TCP communication between these systems, right? And you can then clear out any filters that are on and go back to the original one, come up here, and then just start watching. And you can start to look at where traffic are flowing around your system, right? This is what we do here, guys, right? Gan, thanks for showing up. SK, thanks for being here. So, anyways, we were here. We were looking at the TCP header, and there's this IETF. If you want to go read, again, if you want to go pull up your gender neutral pants, here is. Sorry, I heard something downstairs. Probably my wife dropping a box or something. She's down there doing puzzles. But you can come in here and you can read the specification, and you can actually go and look at how TCP fits in with all these different pieces. This is the technical implementation of the tool. Now, do you often need to come down in here as like a systems engineer or something? No. But when you're first learning and you first want to see kind of how this stuff was put together, this might be useful. Some of you might not find this useful. I would tell you this is a super useful tool. Come in here and watch how traffic flows around your network. This is big. You guys can even pull this out. You can pull data out of your Linux boxes, right? So you could do TCP dumps. TCP dump out into a format that's actually readable by TCP will by default write out to a format that's readable by Wireshark, right? So you can dump data out and then look at how the traffic's flowing around in your network. All right. So, by the way, guys, it was a lot cooler today in Phoenix than normal. So it was, I think it was only like 103 or something. It's breaking summer. Summer's almost done. Saigama, it would be similar. VPC flow logs from AWS are interesting in that they just give you 9 fields, right? And for people that want to go, you do need to know your VPC flow logs pretty well. If you're going to do, you're going to get your cert in this, you need to know your flow logs pretty well. Specifically, you need to know the fields that exist. And here's the fields that are accepted or rejected. They'll show you a bunch of things. So typically you're going to get an accept or a reject. They're going to tell you a bunch of different things over here. One is this is the interface of the device that it was going to. I believe this is a source and the destination, and they walk you through what all these things are and why you want to know them, if there was any data that was skipped, that kind of stuff. They need to, yeah, okay, they have it all here. And then there is a structure here for what these all are. The source port and the destination, this should be, yeah, so this should be the source address and the destination address at the IP layer. This should be the source port and the destination port. So in this case, was this SSH traffic? Yeah. And then they should talk about what these things are. From this to that makes sense. Man, guys, I can hear the storm going on outside too. I think we got a bit of a dust storm coming in. Then they show some ping traffic and that kind of stuff as well. We're going to get into ping stuff here in a second as well. But suffice it to say, you've got like what a header kind of looks like. You've got the IETF if you want to go dig into that deeper. Yeah, we get them out here, SK. They're just some stuff, just some dust storms that blow in or whatever. All right. So there's also a UDP header. And look how small this little UDP header is compared to TCP header. So look, that's the same source port and destination port. That's still 32 bits across. There's a length of it because it can be variable length. And then there's a checksum of the whole frame. So this was, multiple lines. I think we counted up before. This is like 64 byte header. And this... So that's 64, but I think it's bytes header. And then this down here is like 32 and 32, so that's 4 bytes and 4 bytes. So this is like an 8-byte header. It's pretty short, right? But if you want to go read more about it, here's the IETF.org RFC, and it talks about how UDP works and why UDP was picked to be the way it is, and then it gives you the technical implementation, and you can go read about it a little bit. Right, and there's all kinds of RFCs out there that you can read about each of these different pieces. All right. So then, I said TLS operates at this layer, right? So at layer 4, we have transport layer security, and transport layer security is this idea that we handshake between a client and a server, and we establish a trust relationship. The trust is based on a certificate authority somewhere, and that certificate authority gives, it generates, the certificate authority generates with its within its own system a public and a private certificate. The private certificate and the corresponding key go to the server, and they never leave the server, and they're never shown to anybody. The public version of that key insert stay with the certificate authority up here somewhere in the world. So when this client wants to verify that that server is who it says it is, it goes out to that certificate authority and it downloads the most current version of the public cert. Then it says in this case, hello, and then right here it encrypts something with that public version of the certificate and sends it over here. And it says, hey, here's an encryption that I'm sending over to you. And the server says, well, I can decrypt that with my private version of that key that nobody else in the world has, and I can send you back the original data. And when the server gets that, it's like, yep, that is who it says it is, and then they negotiate right here what certificate they're, or what sorry, symmetric key they're going to use, right? Calculate a symmetric key, and we have a secure channel. I know that I'm talking to one device. That device, well, that device knows that it's talking to the one person who originally sent the message, and then from then on they can communicate with no chance of anybody else getting in between. Yeah, SK, have you been here before when I talked about the little primer you guys can go do on that? If you need help with certificates, I'll bring it up if you guys want. Do you guys want the place to start for all this? This is it right here. It's called Solving the Bottom Turtle. I would go put this in my notes, right? I'll put this over here. Solving the Bottom Turtle. And then you jump down here to page 42. And it says, actually it's 41. It's a brief overview of X509. And he walks through, well, so it's a bunch of authors, but they walk through how this works. They explain how we can have secure communications between two people. And they talk about how the key does that. So this is a really good primer for how this all works. If anybody struggles with this, that's where you go start. How do we do a certificate revocation? Like there's a compromised service. What do we do? There's a lot of good information in that. All right. So PKI is commonly known as, so that's private key infrastructure, commonly known as secure socket layer or transport layer security. People use these interchangeably, although SSL really isn't used anymore. If you run into any server that's using SSL, it really should be TLS 1.3. SSL should be deprecated out. I remember deprecating my last SSL out of my servers back in 2017. So you really should be at least on TLS 1.3 nowadays, right? Browsers using that can ensure the authenticity of the server. Remember, it's non-repudiation. I know I was talking to that server. Nobody can say that I wasn't. And then I know that the data is encrypted between the two endpoints because we established a key after we established that I was sending data directly to you and you were sending data directly back to me. And we're the only two that could possibly know that symmetric key that we had determined that we were going to use. Here's that example kind of written out. Certificate authority sends down a SSL TLS certificate. It's digitally signed. That never leaves the server. It stays there protected. Then some client comes along and they can download the public version of that all they want. Once they have the public key, they can send data over, and then they can establish that communication channel, right? That's what we were just talking about. Public key is used to encrypt some generic data that we just want to send over and say, okay, buddy, if you can decrypt it, we can talk. And when they decrypt it and send it back to you, you go, you're the only person in the world that can possibly have that private key because I trust that certificate authority that I downloaded the public one from. And then it goes. Some audio came down my pipe. I don't know what that is, pre-breakfast banana, but that's funny. All right. So let's do a layer 4 example in Wireshark, right? So I'll pull up Wireshark. And again, TCP. I can come in here and I can look at any piece of this. I can see if there's timestamps on it. I can see the sequence and acknowledgement. I can see where they are over here in the traffic. I can see the payload, which is not part of the original header. And I can go see all of this different information. The sequence number, the acknowledgement number. And the acknowledgement number might be some giant number like this. But relative to this communication, it's acknowledgement number 33 from the far end. The generated number is some huge number, right? Because I said we have billions of numbers we can use. But the relative acknowledgement to the communication in whole is this is the 33rd time that we filled up whatever the layer 5 window is before we need to get an acknowledgement back, right? So there's all this stuff here, but this is all the TCP stuff. We can see the source port, the destination port, and we can even come up here and we can start filtering more, or we can look for specific types of ports. There's all kinds of things you guys can do with this, right? In fact, there's one I like to show you guys sometimes. We can actually open, so let me just open a recent one. Show you guys my my creepy one here. And continue without saving. And this one has a voice over IP call on it. And we can replay back possibly the creepiest voice I've ever heard in my life. So listen to this. Hold on. This one's creepy.
Hello, world.
I don't know if you guys can hear that.
Hello, world.
That is one of the creepiest hello world voices I've ever heard in my life.
Hello, world.
Oh god, I'm gonna have nightmares. But anyways, you could replay back voice over IP calls if you're using real-time transport protocol. RTP is real-time transport protocol, as opposed to SRTP, which is secure real-time transport protocol. Yeah, I can't do that for you, Dave. Yeah, that's scary, right? But this is a capture I did in one of my college classes, and real-time transport protocol, and then we secure it with secure SRTP, which is secure real-time transport protocol. But this is a protocol that fits in with UDP. So you've got UDP, and then you got real-time transport protocol on top of it. And this can allow for the passage of data for like voice over IP calls and that kind of stuff. Most of you guys that have used voice over IP in some way are probably using some type of real-time transport protocol over the top of it. It used to be, before RTP, it was H323, or yeah. It's one of those protocols that we used to use, but it tends to all be RTP nowadays. All right, so anyway, so that's Wireshark, and the most important thing I can tell you about like using that tool Wireshark is you just gotta go spend time with it. I am not a network engineer anymore, so I don't spend nearly as much time down in there as I would if I was like a full-time network engineer. I would probably spend all my time in that tool. But as I'm not anymore, I'm a systems engineer and a high-performance compute engineer and just a general Linux engineer. I don't spend a lot of time digging into that, but I can tell you, if we have a real problem between some systems communicating, I will pull that out and I will do TCP dumps and figure out, why is my system not able to communicate to this other system, right? We use the tools that we can first. We ping, we make sure resolutions are happening in names, we make sure whatever those things are, and then we start digging into the heavier tool. You call out a bigger, heavier tool for whatever type of problem you run into. I always use that analogy of, if you toss somebody the keys to your truck and tell them, hey, go grab everybody ice cream, and the truck just starts, they're just going to drive off. But if it doesn't start, then they're going to have to get out and kick the tires and look under the hood and go, oh yeah, the engine's not engineing, that kind of stuff. It's funny that this thing has no idea what I just said. All right, anyways, so layer 3, what's layer 3 doing? It's doing routing. Routing is path determination and packet switching, right? Those are the two things that routers do. We can also limit traffic with access control lists and their logic. Access control lists come in standard and extended varieties. If you go the Cisco route, standard only filter on the source address. Extended can filter on pretty much everything else. They can filter on source, destination, source port, destination port. They can filter on pretty much anything like that you might want. TCP or UDP. And then we'll talk a little bit about IPsec and how that tunneling works. All right, I'm talking a lot, so I need to drink a lot of water. All right, so this is a header, what we call, that should be, why is that, hold on. Did that? Hold on. Those are data. Whatever. This is okay. Sure, it's a diagram for a packet. All right. So packet is what we use as what we call the protocol data unit, the PDU of the network layer. So the header diagram packet, and IPv4 packet has 32-bit addresses. So you've got a source address, which is 32 bits long, and a destination address which is 32 bits long. Those 32 bits are what we've been talking about kind of this whole time, all the way from back at the beginning when I was talking about subnetting, right? There's all this other stuff that's up here. There's the version. There's only two versions you're ever going to see in, well, there's only one you're ever going to see in IPv4 packet, and it will be, so this is the, so it's 0000. So if it's 4, you're going to have 0100 right here. Then there's an IHL and the type of service and all kinds of different things that might be in here. The protocol that will drop in here will be related to the transport layer protocol that this datagram is carrying. And that's because some inspection, again, for routers and other things, can inspect what's happening at the transport layer because it's been reported down to the layer 3 that they're looking at, right? Things don't ever really leave their if you want to call it like their control, like what they control. So routers are looking at layer 3 and the protocol is down here, so then they can filter based on things that are happening at a layer above what they care about, if you want to think of it like that. If this protocol wasn't here, network devices would not be able to determine what was happening with the transport layer. All right, but we'll see that here. There is a data tracker IETF, so I have all these so you guys can just have them. By the way, some of you might be wondering if this is up somewhere. This is up in the Discord, so if anybody needs this talk, this is up in the Discord, and I have the original talk up on YouTube for this as well. All right, but anyways, here's the IETF protocol, and then you can walk through and you can go see how this started. How IP works, what the components were of it. Right, this is the kind of stuff you read when you want to go to sleep at night. You're like, oh, how does this all work? Oh, I'll just... And next thing you know, you're asleep because you were trying to read a frickin' IP. But when you're first learning, this is excellent material to go dig into and spend some time with, guys. There's some good value here for you. All right, so anyways, this is something you can go read about and study and look at. But honestly, the best way I think to do it is to come in here and go, well, what is this? This is IPv4. So look, it's 01. That's the 421. So it's 04. That's version 4. That makes sense. That's the only thing it should be there. Then there's information here about time to live. How many more hops does it have? There's some checksum. There's a source address and a destination address. So this was a 192.168.1.50 device talking to a 192.168.1.52 device. Things I know about that, those are definitely going to be in the same network, right? I know that they are definitely internal non-routable IP addresses. Anything in 192.168 is. And I go, okay, so this was internal network traffic that never left the network. So, these were just two devices talking on the same network, right? All right. And we can come in here and we can look at all these things. There's a don't fragment on this. Maybe that don't fragment was set because, one, this is a small enough frame, probably a small enough piece of data that we can do that. We can look at the overall size of this. There was, this was 214 bytes on the wire. So this was a pretty small frame in general. Now you might say, well, Scott, why do you care that it's 214 bytes on the wire? Well, one, I see that, one, you got to think about what's the maximum transmission unit on an Ethernet 2, frame by default. Anybody know? You probably run into it more than you think. Yeah, 1500, right? Can that be changed? Absolutely. But what I see here is I see a device. So who determines that something's not fragmentable? Well, actually layer 3 does. But I've shown you guys this before, and we could do this if you want. But if I set a don't fragment here, and it is over 1500 bytes, actually if it's over about 1480 bytes because of the header, what's going to happen to this packet that tries to come down, and when it hits this layer and tries to get chopped in half, it says, don't you dare chop me in half. Well, traffic doesn't flow anymore. Veer Singh said, "Hi there. You're probably all packed up. Do you have any plans to finish home lab from scratch?" Veer Singh, yeah, I probably. I mean, I've never done a full home lab from scratch type video or anything. Um, I just kind of run things in the lab as I kind of go. I've shown you guys how to start those kind of things. And I do know that sometimes down our Linux group, we'll actually on Saturdays we'll build stuff out for people or work with people on stuff. So I might just say that's the best way to do that if you need any of that, because I don't. For me, I already got the lab set up, so I'd probably. I have too many things in here that are actually being used to blow my lab away. Like I have too many things in here that I actually use for stuff. But maybe one of these days, I can blow a lot of that away. I know that I've said I will do it, and one day I will, but it's probably not going to be this day. So, yeah. IPv6 is a little different. It's huge addresses, right? Those are 128-bit addresses, which is 4 times bigger from a number perspective here, but in actual number of addresses is astronomically bigger. You go from 4.3 billion addresses to literally trillions upon trillions upon trillions of addresses here. It's a huge number. Go put a 2 × 128 in Google and see what it gives you. It's huge. It's a huge number. And they talk about it here a little bit. One of the things that's important to understand is IPv6 has a few things built into it by default. It has geographical organization. So IPv4 was not built for anything other than working. So IPv4 is not tied to geographical locations. It is loosely tied to geographical locations, but not really. Not 100%. IPv6 is. IPv6 flows the data in regards to where it's being sent from planet Earth. Always. And everything fits, so there's no problem with natting and any of that kind of stuff anymore. Other things that are important to know is, where do they have it here? They have it, yeah, so they've got this next header, and I believe, because you can keep adding modularly more headers to this, and what you can get is security is built into IPv6. Security was not in any way, guys, built into IPv4. Not even a little bit. Not even kind of. All it was designed to do was route packets and get them there, no matter where there was. And it was designed to work even if half the country was taken out with nuclear bombs, because it was developed in the late 70s when we were in the midst of the Cold War still. So, all right. So, yeah, IPv4 to IPv6. This is things I was talking about. So, what are the differences and improvements? IPv6 has way more addresses, obviously, than IPv4. Geolocation and security are big parts of it. All right. And eventually, when we get more and more into like space travel and other stuff like that, there is enough addresses in IPv6 to support even outside of geolocation, because there's so many addresses in that space. As long as it's organized properly, you'll be able to use that to address things even off of Earth, right? All right. So, layer 3, we're still down at layer 3. A little bit of history. Firewalls are part of, they used to be an older device called a packet internetworking exchange, or some people would call them gateways. And they were the device that sat at the demarcation between your network and another network. Exunyum, you said, are you saying if my ISP has my network NAT, even then I can reach it consistently via IPv6? I'm not sure what the... Oh, I see what you're saying. It would always be there. Yeah. So they may have... There may be some type of NAT translation going on for... Yeah, I mean... There are internal addressing that are still available to be used. Um, you have to check that because I don't know that as well. But I know where you can go learn more about IPv6, right? Because there's those certs. Mess up your SSH. Yeah. Do you know what my solution is to that? My solution is a dynamic DNS. You probably have dynamic DNS, and what is your device when it comes up, it just goes and registers its IP address. So like for me, I go to my home lab. So my remote home lab from anywhere on planet Earth is prolug.asuscom.com. And that name always registers back to my home address, my home IP address from anywhere, right? So then anybody can try to get in, and most of you guys that know me know that I monitor all that stuff and I track everything, and people get locked out forever if they mess with the stuff, and there's all that kind of stuff, right? But the point is, yeah, you can. Back to firewalls. So firewalls tended to be a device that sat at the edge of your network, right? The edge, and the edge has changed over the years, but they are still edge devices. Yeah, what you want to do is get this. So you want to go. So what is dynamic DNS? It's you probably have it built into whatever router you have. But if not, there are open source dynamic DNS that can work with your I've never used one of these, but I know they exist. I know they exist out there in the world. Yeah. So there's tools out there. I couldn't tell you which ones were good, but I do know that they exist. Yeah. This is the tool that you want to work. I've been using this for 15 years. I use this to just get to my home lab from wherever. Like when I'm down in Mexico doing stuff, I can connect to my stuff from anywhere in the world. So that's how I do it. Okay. So, yeah, so different autonomous systems, and this is how we protect. Okay. So then, like, we've got an important concept here, and this is probably how a lot of your home labs work, or your home systems are stateful versus stateless packet inspection. It's a very important thing to understand. This feeds up into your understanding of how the cloud works and how cloud vendors give you the ability to protect your own stuff, right? And some of you guys, I mean, I don't really play it up a whole lot, but I do have like 5 of those AWS certs. I understand AWS pretty well for a guy who doesn't do that professionally, really. But I did spend quite a lot of time building stuff in AWS. So stateful keeps track of traffic. Stateless does not. That's an important thing to know. But stateful works like this. You're in here, and this is your machine. This may be me in my home lab. And I want to go request a web page from this, lucent.com. And I go to them. And as I go to send traffic out on port 80, you guys got to think about this for a second. As I go to generate this right here, whether it's a TCP or a UDP header, it's going to be TCP for this traffic. I'm going to use the destination port of 80 going out to the web page, or 443. And my source port, you're going to say, well, what the heck is your source port? Your source port is a arbitrarily just set up port on your machine, typically over port 5000. Like 5,000 to like 1,500, or 5,000 to like 15,000 on a lot of systems. And it depends on your vendor and stuff. In fact, that port is part of how people map. Yeah, it's an ephemeral port, right? It's a port that's past the well-known ports typically, right? Well-known are 0 to 1023, right? it's 1023 rather. But anyways, so source port is just going to be some arbitrary thing. But what will happen is as that gets read, the firewall is going to keep a record that your device with a source port of like 5183 went out to port 80 to wherever this IP address was, because you're using IP address at this time. It's already, DNS has already happened. DNS resolution came out here, came back. Now you're making the request. In the cloud, ephemeral port exhaustion can be a problem. I can see that. I can see that for sure. So, he goes to send something back, and when he goes to send it back to you, he sends it on that port I made up, 5183. And as the firewall here sees that, and it goes, yes, this IP address for this, whatever was resolved from DNS is coming back. And he wants to talk to that device on 5183. Thank you, Robodom. And he says, I'll let you through, please. It's like a bouncer giving like you have like a little wristband at a nightclub, and you can leave and come back here. But anybody outside is not able to get in. Their stuff's just dropped. And that's typically, we used to call that in the Cisco world reflexive access control lists. So they're access control lists that open for a port to come back through. Remind me sometime, I'll tell you guys that story about how I did a class in college. It was a 400 level class, and I had to teach something. So I taught how to take a little Cisco router and turn it into like a PIX firewall by setting up stateful access control lists on it. And, this is the whole story, I guess. 2 women in the class complained that my 400 level bachelor's degree in network communication management at a technical college called DeVry, they complained that my presentation was too technical. They never got jobs in the field, if anybody cares. In fact, they sued the college because they didn't learn anything. And I think they're actually, I use those 2 women as examples of people who just refuse to do anything on their own. They get in a college class and they sit back and cross their arms and go, teach me. And then they will never make any effort for themselves. And it's like, they're never gonna make anything of themselves. And they never did. Neither of them ever got into IT in any way. And I have a friend who, he's working on his doctorate in economics, and he likes to say, you honor the degree doesn't honor you. And I kind of agree with it. Like, you're going to be the one who makes that degree worth something or not, Yeah, Robodom, you wouldn't believe it. They were like, it was too hard. These were the same ones. Don't even get me started on that. I'll be on all night. All right, let's talk about access control lists, right? So I said earlier that they're standard access control lists, and they can only deal with source IP, or they used to be called basic or standard. And then extended access control lists can do network layer, they can do transport layer protocols, they can do destination, and they can do TCP or UDP. Forsaken failure, everything is too hard. I like that. I will tell you guys something. So when I went to the college, I had 49 credits from my, before I left the Army. I had 49 credits at Pikes Peak Community College up in Colorado. And I came back down to Phoenix, and DeVry took 14 of my 49 credits. And I had a CCNA. I had passed my CCNA. So I'm like, okay, cool. And they're like, all right, well, you've passed these classes, but we're going to put you in this one. And I was like, guys, I was like, and this was 22 years ago. Hey, Blazebits, how's it going? How was the stuff? Were you guys doing tech stuff? Cookie Monster. I'm doing my little primer on Linux or on networking, and people got me into some people in college that really bugged me. And I was telling about these 2 women who they never did anything with their degree, and then they sued the college because they didn't learn anything, and it was all terrible. Oh, fighting with PowerShell and Active Directory, nice. And what they did was I remember this class. They put me in this class, which was it ended up being, so they had taken my 14 credits of 49, and they didn't put me in Cisco 3.4, but they put me in Cisco 1.2. And the way that Cisco used to teach their classes was 1, 2, 3, 4, and then go take the CCNA. And then, so check this out, right? So this is what happened. So I'm in this 1-2 class, and I remember the teacher was Bruce Frederick. I still keep in touch with him. And one of these days I'm going to call him up and ask him about this, because this fucking bugged me to no end. I'm going to tell you guys something. We have 8 weeks of class. So 8 weeks of class, right? And the first week of class, he gets up there and he shows how to do subnetting, something that I could have got up there and taught, right? And I knew the subnetting well. And these women raised their hands and they took the whole 2-hour class asking questions about subnetting. So that was the first week of class. The second week of class rolls around and he starts moving on to other stuff. And those women raise their hands, one or two of them or both of them. I don't know. They're fucking like this amalgamation in my head of just fucking everything that's wrong in college, right? And anyways, they raise their hands and they ask about the subnetting again. So he spends 2 hours of this class again explaining subnetting to them. This went on for all 7 classes. The 8th one was just the final. If they could have, they would have interrupted the final to ask fucking questions about subnetting. They never bothered. Those 2 people, doesn't matter that they were women, but those 2 people never bothered to go learn that shit on their own and be ready when they got to class. And that's what bugged me about them. And then again, how they got all the way up to a 400 level class 2 years later and then were there to say that my stuff was too technical, it bugs me to no end. all right. Anyways, guys, I'm not trying to be PC or non-PC there. They happen to be females, you know. All right. These are the things that access control lists can filter on. Standard access control lists can only do source IP, and extended access control lists can do all the other ones. All right. Yeah, I passed my CCNA in 2002 when I was still in the Army. I had a rifle, and I knew how to program the shit out of switches and routers. I didn't know anything about what a server was back then. All right. So this is the access control list. I call this the coin sorter problem. And this is why I call this the coin sorter problem. And only Scott calls it that. You see that down at the bottom there? Nobody else calls this the coin sorter problem. Only me. But I'm going to explain it to you like this. What if you went to a coin sorter and you had a bunch of dimes and you had a bunch of 50-cent pieces and you had a bunch of nickels and pennies and stuff and you poured them all in and the thing searched first, the first thing it filtered for was 50-cent pieces. Now, if anybody here is not in the U.S., the 50-cent piece is pretty much universally the biggest piece in American coinage. The 50-cent piece is big, right? I don't think there's anything bigger than it. Maybe some silver dollars are about the same size. But the point is, if I filtered for the 50-cent piece first, and all those dimes and pennies and stuff were coming in, wouldn't all of them fall in that hole? And wouldn't everything be a 50-cent piece? And wouldn't I be getting paid way more than I should have for all that change? Yes. Yes. So, logically, to sort coins, you have to start with the smallest. And what's the smallest American coin you can have? You're right. It's the Canadian penny. The Canadian penny is about the same size as a dime. I don't know if you guys know that. I don't know if you've ever had like a Canadian penny show up in your normal pennies, but it's about the size of a dime. You were in Signals. I was not in Signals. I was an infantryman. If you're asking me what I did in the military, I was not in Signal. Nope. Okay, so you have to filter by the smallest thing first. So filter by dimes, and then pennies, and then nickels, and then quarters, and then whatever of these other types of coins you want to filter by. Typically like 50-cent pieces, let's say. So the same thing happens with an access control list. If you come down, access control lists are filtered in order. So IP access, this is an extended control list in this case. It's going to deny anything from this source address matched perfectly to this anywhere, to anywhere. So that's anywhere. So we're going to deny any IP from this guy anywhere, right? So if you're this guy, you get blocked out here. You're done. You're no longer playing the game. You have been filtered. You do not pass go. You've been denied. But if you don't hit that rule, you just keep trucking along. And then you get to this rule. And if that rule hits you, you're done. Right? Or like this. Right? Like I'm dead. I died. And then I come down here. And here's the thing. If I get permitted here, I'm also out. I'm happy. I'm gone. I'm not filtered anymore. So you're filtered as you come down through these systems, and as you logically hit whatever rule matters to you, much like the coin sorter, this is why I call this the coin sorter problem, then you get to leave and, like, because once you evaluate that something's a penny, do you ever evaluate it again in coin sorting? No. It's a penny. Get the hell out of here. I don't want you coming back around and being a quarter or something later. Get out of here. Right? And that's the idea of how coin sorters work, and how access control lists work too. Later on, and this is not part of this, but later on, there's optimization. And I spent some time, I think I told you guys early in my career, I spent some time doing firewalls for a school district out here in Phoenix. And there's some optimization that can happen here. Now, the optimization still has to follow that logic of what you want to happen, but you start to look and you see like a hit count and a hit count and a hit count. And then like you get down here, and then one of these, like as you have like you know, maybe 50 rules, one of these hit counts is like 300,000, and all these other hit counts are much lower. So then you're like, well, wait a minute, why can't this one be up earlier so that these things don't have to be applied before one of these many things here gets blocked out? And we start to deal with optimization. And you might say, well, that seems kind of silly. Why would I want my router doing 4 additional things when I could just have it doing 1 if I could move this up here logically? And that's where optimization starts to come in. And then you go, well, because at the end of the day, all systems that we know of on planet Earth are this. Does everybody know what that word means? As an engineer, this is one of the most important words. Infinite is not finite. Finite is not infinite. Yeah, it's a trade-off. This system is fast. It is optimized to sort these coins or access control lists and packets, as it were in this case, and it can do them fast. But it can still only do so many thousands or 100,000s or millions or maybe even billions in 1 second. It can only do so many. And then when you think about it like that, and then you see that I just optimized that something was always doing these 4 things before it got down to here where it was most likely to be blocked, and I moved it up here, so now most of my decisions are only 1 instead of 4 operations. Now you start to have some true optimizations of the system. Yep. You have a finite system. We know of no infinite systems, guys. We know of no systems where we can generate more power and pull more power out of the system than we put into it. It's the same thing with how many actions we can do in a minute. They are always going to be limited by whatever is our limiter here. How fast we can push electrons across circuits. How fast we can do that before we heat up the circuit to a breaking point, right? So that's the. I went far afield, but that's how access control lists work. This is the same thing, but in AWS with a NACL, which is a network access control list, and they do the same thing. They apply the rules in order. These are stateless, meaning if you don't allow traffic back in, it doesn't care. So because network access control lists are stateless, you must create inbound and outbound rules. So look, I allow HTTP in on port 80, right? So this is an inbound rule. I allow port 80 in. In my outbound rules, I would have to make sure that I allow, so check this out. My servers maybe connect out to somebody. In the outbound rules, I'm allowed to go out on port 80. And look at this custom TCP rule for traffic coming back. 1024 to 65,535. And that's from anywhere from 10.00.16. So this device here, and I don't know what the outbound rules look like from this, but let's say I was going on port 80, or let's just say I was connecting to a database even on 3306, right? That's the common like MySQL or MariaDB database. and I connect out, but then I have a custom port back. This is the one that allows that traffic back right here. Those are the ephemeral ports. And some clients start up in the 5,000 range just to not be. So the well-known ports are 0 to 1023, but then there's some other higher range ports that get messed with. So sometimes systems will start higher from clients. You'll run into like the 9,000s. There's some collisions in the 9,000s. The Grafana is 3,000. Loki is 3,100, right? We know that from some of our other labs. And then 9100 is your node exporter, right? So now you can't be using that one. 9100 is also oh, what the hell is that? That tool nobody fucking uses from Red Hat. Oh, Cockpit. Yeah, Cockpit. They're like, oh yeah, everybody. Oh, I know what we'll do. We'll say that all servers should be ephemeral and nobody should ever connect to them, and then we'll make this fucking ridiculous GUI that everybody can connect to. Who the hell? Look, guys, I don't want to. I'm going to tell you right now. Look at this. Hold on. I'm going to show you something in my home lab. I don't want to connect to all of these servers like this. This right here would be, and I only have like 30 servers in my home lab. I would, if you said, Scott, go right now and do some work on each one of these servers individually like this, I would tell you I quit. And you'd say, you can't quit. You're just a streamer and you're working on your home lab. I would say I quit life and I quit doing this because I would not do. This is insane. This is this long. This is boring. This is terrible. Right? Do you guys see what I'm saying? This is terrible. But that's like what they decided to do on Red Hat. I'm like, what the hell are you guys doing? Literally, everybody just wants to do this, right? Everybody wants to do this. There's going to be a few errors here, right? That's it. That's all I want to do. I want to hit all my servers. There's going to be like 6 nodes that don't come back because the keys. Don't worry about those. Yeah, those are key. Those 5 are key problems. But all the other nodes are going to come back, and I can manage and maintain all my servers like this. Why the hell would I go? Look at all these lab boxes I got. Jeez. That's how I want to maintain things like that. I don't want to do it. Anyways, all right. But anyways, the point is, not all clients are going to use all those ports. That's what I was saying. All right, I know I'm getting loopy because I must be getting loopy because I'm like going far afield often. But so let's go look at Wireshark again. Wireshark has all this good information on the IP layer right here. We can see that the protocol above this is UDP. Now that's up at layer 4 now, right? So we're at layer 3 down here at network. But it's telling us that the above layer is layer 4 doing UDP. It's not a TCP packet or segment up above us. It's a UDP one. We see that it's 214 bytes, so we see it's well under the maximum transmission unit. And then we can go start digging in on, okay, if we had any services, if we had any flags here, is there a reserved bit or don't fragment or more fragments are coming, right? We can see all that information. And again, most important stuff, source and destination address right here. But you can then go see, and then you can see information about this. And we may be able to follow this UDP stream and then see what each of these things were doing as they were sent across the network, right? G711 is one of our encoding. So if you said, hey, what the hell's that G.711? You come over here, you go look here, and you go G.711. What is that? It's a codec, right? What is that codec? And then you go read about it. And this is what, this is what I try to explain to you guys, is that like all of this stuff goes and points somewhere else. And then you go spin off and spend some time reading about how this works. And oh man, look at how long this thing's been around. It's a pulse code modulation, PCM, of voice frequencies. So any of you guys that have heard me talk about the analog to digital conversion, analog is a perfect wave. My voice may not sound perfect to you, but I assure you the wave of analog data that is traveling is a perfect curve. Now, it is perfect in whatever way that I have generated it, but we sample that down to get digital samples to send it over the network. And then when it comes back to the other side, before it gets sent to you guys, it gets turned back into as close a representation of the original wave as it can to be my voice, but it is not perfect anymore. So when I say my voice is perfect, I'm not saying that, oh, it sounds perfect. What I'm saying is my voice was perfect before it got chopped up into this digital thing and sent over to you. Does that make sense? And then does it make sense too that the more often you slice this or sample this, the more precise my voice is going to be when it comes back on the other side? Yeah, the Nyquist sampling theorem is actually something that comes into this, absolutely. Then we start to talk about lossless and different types of compression. And then you spin off and go, oh, shoot, I want to go work in telecom centers and stuff, right? Then now all of a sudden you're doing all this other stuff. But G711 is a way that we can pass audio signals in the frequency band of 300 to 3400 hertz, which is the typical band of the adult human voice. Some people, some women can be above that. I guess some men could too, technically, but most of us operate somewhere in this range. And I've told you guys before, I'm on top of many types of engineering. I very much enjoy signal and data and audio style engineer. I wouldn't call myself an audio engineer because I don't do that kind of stuff. I'm not like Sid Hennessy or whatever. Sid Heresy, whatever his name is. I like to go hop in his channel every now and then. But he does like audio, like true audio engineering and like big, performance type stuff. Whereas like I like to do the signals and how they're being sent and taken apart and stuff. Guys, there's a lot of tools that'll do this for you. A lot of tools that'll teach you this stuff if you want to play with it. All right, but anyways, there's that. So I just showing you guys all this stuff you can find out by going and getting into Wireshark. You guys got to spend some time in there if you want to get good at it. You don't just learn all that stuff over time. Yeah, Python has some tools for signal engineering as well, for sure. All right, so layer 2 concepts. There it is. Yeah, Sid Heresy. There he is. What's going on here with layer 2 concepts? We've got switching. Switching is typically done down in hardware. Then we've got that physical addressing we were talking about. Physical addressing is 48 bits total if we're talking about MAC addresses. The first 24 bits are the vendor portion, and the last 24 bits are the host portion. Then we got address resolution protocol, ARP. How does my system know the mapping of local hardware addresses to IP addresses? So my system will try to tell me, like, your system's trying to tell you about as much as it can. ARP-A. Look at all this stuff my system knows about. Look at all these different things in my home lab that are maybe known. Then some things are unknown. Like, I don't know who this is. Actually, that's funny. It doesn't know this device, but it knows its MAC address. But this device right here is actually my laptop. And this laptop's talking to this thing almost all the time when it's here. But then it's mapping for me the host names that it has to the different IP addresses that it knows for them and their MAC addresses over here. MAC addresses are very important for data traveling within a network. So when your system does, let's talk about something real quick here. IP adder. Let's see if I can do my whole IP adder and still see that. So here's my Ethernet. Here's my internal network, 192.168.11/24. Now, does anybody know why I only highlighted 192.168.11 when I have a /24? Does anybody know, like as a network engineer, why I only highlighted that? Or why I only care about this over here? Also, Doc, I'm sorry I'm missing all your stuff. I might have missed your... Oh, also, yeah, Doc, if you're in Discord, it'll tell you when when I go live or when the other guys go live. All right. I feel like I kind of move fast sometimes, guys. I know. So I realize, like, some people are probably like, oh, I don't want to try to answer, but okay. The reason I only selected the first three fields here, the first three octets, is because with a /24, they're the only ones that matter to determining the network portion. Yeah, that's exactly right. That's the network portion. So what that means is everything in 192.168.11 that's up here is in the same network with me. My machine knows that, and my machine knows that via a process called anding. 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 It's the anding of bits. We don't need to get into that right now, but if we want to go jump back up to my tables, I can show you guys how anding works. But it's just a logical process. Anyway, so it knows that everything in 192.168.11 is in the same network with it. So look, lab 5 right here. 192.168.11.155. When my system goes to send, if I tried right now to ping lab 5, my system will go look at the network right here, 192.168.11, and it would say, aha, that is clearly 192.168.11 is clearly in the same network with me. 192.168.11, 192.168.11, it's in the same network with me. So, since it's in the same network with me, I'm going to go and look up its MAC address, and as I formulate this stream of data coming down from, my ping is starting at a layer 3, technically. And as I'm formulating this and starting to drop down into my MAC, I'm going to go ahead and give from my address resolution protocol table, ARP, I'm going to go ahead and put that as the destination MAC, because it should still be within the same hop as me, still within the same network as me. I don't know all the pieces underneath, but I know that that's the MAC to get there. So then my system does not try to send it. When I go to send this, my system has now made a choice at the IP layer to not use the gateway. So I will use its IP address, 192.168.11.155, up in the network portion. So in my packet, I will use .155. If, however, so check this out. If, however, I had seen one of these guys are all on my network. Yep. They're all on my network. But if I had seen, however, like this. If I had seen this guy, 142.250.188, does that map to this as far as the first three places are significant? Are they the same? Is 142 and 192, nope, already different. So they're different. So I will not even try to look this up in my ARP table. I will simply send this out my default gateway if I have one. So my default goes out this port. So I'm not even going to look this one up because he's not in my network. I don't know what his I already know I don't have his ARP table or an entry in my ARP table for him. So I will not look him up, and my frame at the network layer, or sorry, at the data link layer, is simply gonna be this guy's IP address, or this guy's MAC address rather. Where's he at? Should be the one. Where's the .1? Do you guys see him? Here, this guy. I'm gonna use his MAC address and his IP address, and that's how I'm gonna send it out. So your device uses this process of anding at layer 3 to know if something is in the network with it or outside of the network. And then that determines whether or not it looks up a MAC address and tries to send it locally or not. All right. You can dig in on how that works, and there's all kinds of stuff written on that you can do. But that's ARP, Address Resolution Protocol. Then there's a problem with redundancy in non-hierarchical address space. So what I mean by that is if you're using multiple switches, once we started to want multiple switches, we had a problem where we needed a tool that would allow spanning tree protocol to work. Then there's another thing that needs to be spoken of at layer 2, which are VLANs. They're 802.1q tagging. So at the frame layer, we tag for what's called a virtual local area network, and then we can expand our local area network so that devices can only talk to other devices. yeah, Gan, hopefully this stuff's useful to you. I mean, that's the goal of this, is to walk you guys through it. And again, I tell you guys, even if you just have a notepad open and you're writing stuff like, you know, and you go look it up later, the heck is an 802.1q? And it might surprise you to know, or it might not surprise you to know if you've ever dealt with Cisco, that there are a whole bunch of ways that 802.1q works. Different vendors do it different ways, and Cisco has a proprietary way that they do it called ISL. So now you're like, wait a minute, hold on. So Scott, if I have a completely homogeneous network, what does homogeneous mean? Everything's the same, right? And heterogeneous or whatever is a different network, so a bunch of different systems together, right? But if I have a homogeneous network of all Cisco devices, I can use ISL, and ISL is more efficient than 802.1q. But I can't do that if I introduce even one other device into that network, which is, by the way, part of the reason why people use proprietary protocols, is to get you. But they're also more efficient, right? And we've had that, man. We've had this over and over again over the years. Like, do we use proprietary? Do we use non-proprietary protocols? Most people are fans of open protocols and open non-proprietary stuff. I mean, if you look at like an ATX motherboard, an ATX motherboard is a well-known. All those standards are well published. If any of you wanted to go and figure out how to solder up a board and put it into a PCI slot, you could do it. You might have to take some electrical engineering stuff, but for the most part, you can do it. It's that all that stuff and all the pins and everything is completely open, and the protocols are out there for you to use. All the sizing of how everything connects is all out there for you guys to use. So, anyways, we're not going to get into that right now, but just know that there are proprietary protocols that mirror what 802.1q does, and they are more efficient, but only if you're in a what we call a homogeneous network. All right, so those are kind of like some layer 2 concepts. The header of the frame. The frames are the protocol data unit of layer data link. You can say protocol data unit, PDU, or protocol data unit. I don't care. The first 8 bytes are what's called the preamble. The preamble lets you know that something is being sent, and this harkens back to the first 8 bytes right here. This harkens back to the days of CSMA/CD, which is carrier sense multiple access with collision detection. This comes back to what we used to look at when there were collisions on networks. Typically, the preamble lets you know that something's being sent, and anything else that senses, because that's what carrier sense multiple access with collision detection is. When anybody senses that the line is being used, that the circuit is open, well, at this case, the circuit is now closed and it's sending. The preamble lets them know that traffic is coming, and then there's a destination address, there's a source address. Those are, again, 6 bytes or 48 bits long each. There's a type field that gives you some information. There's data between 46 and 1500 bytes, but typically it's got to be just under 1500 bytes. And then there's 4 bytes at the end for what's called the FCS, or the frame check sequence. There are a bunch of different frame check sequences that you can go read about, and they're actually really fun. Like what we call the sorry guys, I gotta drink more water. Oh gosh, what the hell is the name of that? Hold on. Let's go Google it. So frame. Hold on. It's going to bug me when I see it. So they explain how it works with a cyclic redundancy check. But there is... hold on. Do we have error detection? Look, that's why I tell you guys you can go really dig down into this. But no, hold on. The thing I want to show you guys for code, parity bits, but it's whether or not they're positive. There's a term for it. Even parity and odd parity. Yeah. So an even parity bit or an odd parity bit would ensure that things stay even or odd based on, so you have 7 bits of actual data, and then the last bit is simply there to make sure that they're either even or odd. And you say, well, why the hell would that matter? Well, look, if you had 7 bits of actual data going, and look, you're sacrificing, when you use the 8th field, like, just think about this as an engineer real quick. If you use the 8th field of something, right? So you go 100 divided by 8, right? So you use the 8th field of 100% of something, you are losing 12.5% of your efficiency, right? Of what you could send, because you're sending 7, and then the last one is only there, guys, only there to make this even or odd, right? That's an interesting thing. So even parity bits and odd parity bits. And again, you can go dig down into these. Different protocols use these. Different protocols use them further down the line. You can go look at them. But these are one of the simplest forms of error detecting code. Either we keep it always even or we keep it always odd. And then we just need to know that for our parity bits. So you can spend a whole bunch of time digging into that if you want. But remember, look at all this. I mean, that's 12.5% of my overall throughput is being given up for low-level error correction at the bit layer. Do you guys see that? That's a lot to give up, guys. 12.5%? Really? But it's the way we used to do it. We give up, so as things have gotten more efficient and better, we do less and less at the lower layers and more at the upper layers. So it makes our throughput higher. All right, anyways. Switch management. So, like I said, when you just used to have a switch go from, and you didn't have redundancy, there was no problem. But now, I want you guys to think about this. This is no longer hierarchical. So, there is nothing, well, it was never hierarchical at layer 2. You don't have just a data flowing over one link. Now you have multiple links. And now, you've got a problem where there's multiple paths that are correct between E to F, and some of them loop. And the fact that some of them loop and there's no default gateway because there's no hierarchy causes a problem. So what we do is we use the thing called spanning tree protocol. Nowadays we're up to rapid spanning tree protocol, and surprise, surprise, Cisco has its own proprietary version of this as well. But spanning tree protocol, you use a BPDU, which is a bridge protocol data unit, to elect a root bridge. All of those devices are going to flood. It's going to be a BDPU flooding and storming until they figure out which of those devices is where the data should flow to. So they elect a root bridge, they elect their root ports, then they elect their designated ports, and then they go ahead and turn off their other ports. So what it physically looks like, this is blocking, listening, learning, forwarding, and then we get to where we're working. But if you look at this, spanning tree protocol can take up to 90 seconds when you're doing all this before traffic is working. Now, 90 seconds is a minute and a half. 30 years ago, and even when I first got in the field, 90 seconds was fine. Fine, whatever. 90 seconds for a network to come up. Nowadays, some of you guys that are in systems world, could you imagine if something took 90 seconds? Could you imagine, if a system went down and the network was like, yeah, it's going to take 90 seconds to come back up. They just sat there and twiddled their thumbs and looked at you. Your network managers would lose their effing minds if something took 90 seconds to come back, right? So what happens here, Exunium, that's true, but it would be detected at the end with a cyclic redundancy check. So that's one of the things. But also, if you have that many errors in only 7 bits of data, you got some problems. All right. Anyways, so look, this is what happens. We elected a root bridge, and I'm not going to give the example right now, but basically, all these things are now going to flow. All the data are going to flow one way. So this data can no longer go this way or this way. It's going to flow this way to get over there. All this data is going to flow this way, and everything's going to flow out the network this way. Okay? See these blocked ports here? But if something changes in the network, BDPUs will be fired off everywhere, And what will happen is then, like, let's say this one got blocked off, then this one would become unblocked and traffic would go around this way. So things are only blocked temporarily until there's a recalculation. Recalculations only occur when there's an error. So STP is defined by IEEE 802.1d, and it prevents traffic loops by calculating paths to avoid potential loops and artificially blocking links, completing the loop. So we block things so all the data flow one direction. All right. Newer versions, there's Rapid Spanning Tree Protocol. Again, it can be converged. When we talk about converging, convergence of networks is when all the devices in the network see the network the same way. That's what the term network convergence means. Rapid Spanning Tree Protocol can do that same process, taking it from 90 seconds down to only about 6 seconds. Trill, transparent interconnection of lots of links, and then SPB, shortest path bridging. I have not used Trill or SPB in my career. I've only ever read about them. STP and Rapid Spanning Tree Protocol are the standards. I was just doing STIGs today on Rapid Spanning Tree Protocol for a couple of devices in my network. Right? All right. Switch ports, there's a bunch of various topics. This is security stuff. Like, use the shutdown command so that unused ports cannot just be connected into, and that's access layer ports. So, like, you shouldn't just have switch ports open out to, like, you know, wherever in your network. Like, people should not be able to connect. You can do switch port security to limit MAC addresses and additional traffic on ports. That'll keep people from plugging in wireless access points. So when a wireless access point connects to a network, that becomes a rogue access point immediately, right? And people shouldn't be doing that shit. And then every MAC address that gets passed through that will try to come in, and then your switch port security will limit how many MAC addresses can be on there. It should only be one typically. Switch ports can be trunked or access modes. Typically, we want to be a trunk. That's going to be forwarding VLANs to other switches. And access mode on a port means that only one 802.1q frame tag is allowed. However, there's a special access mode that allows a second frame tag to be there for 802.1q. Remember, that's the VLAN tagging. There's a special type of access port configuration for most devices nowadays that allows two. And the reason it allows two is because you can have your data from like a network device and your voice over IP line on the same network. And the reason we do that is because then once it gets into your switch layer, then we can start to have and then typically this is when it hits a router, we have QoS applied, quality of service. And then we can allow a certain amount of bandwidth to be passed through or not, right? And then there's another concept. This is really important. This is super useful nowadays, and you got to learn how to configure this for Cisco nowadays. We didn't have to do this 22 years ago when I passed mine, but link aggregation groups, so lags, or you'll hear people talk about, oh yeah, make sure the lag is up. That's a link aggregation group, so you can aggregate ports for speed and high availability between your devices. So I actually really like this. Like, we'll have like a top of rack switch. So a top of rack switch means in a data center, and this is typically how it's done in like a, let's see if we can find some top of rack switches, right? A top of rack switch, if we just look at it, it would be like here. Let's see if we can just open this in a new tab. Open image in a new tab. Yeah, so top of rack switches typically are going to be your connects into other devices, right? And then so you've got this, maybe these switches here, and they're connecting over here, right? And that's cool. You've got communication now between your racks or whatever at layer 2. But what if you had 4 extra ports here and 4 extra ports here, and then now these connects between your things, your switches, maybe those are, your cross connects, instead of being just a 100 gig link, I can have 4 100 gig links in a link aggregation group, a lag, and now I've got 400 gigs uplinked between these switches. And if one of those ports happens to go bad, or somebody happens to chop one of those cables with an axe, I still have 300 gigs of aggregate throughput between those devices. It is super useful. I don't want to say it like changed networking, but it was a big part of how networking works. Look at all this. All I did was search top of rack switches. There's a lot of diagrams out there and things you can see. Maybe you go work in a data center. I actually go in data centers. I'd say a few times a month. I'm in the data center for different work nowadays. I mean, most of it, you guys know, I just sit here at my computer all day and do this stuff, right? Most of the time, I'm just doing this all day, right? Linux, Linux, Linux. That's all I want to do. But sometimes my company sends me places and I got to go do stuff in a data center. All right, layer 2 example in Wireshark. Let's go look at that. Same thing. We're just going to go down here to our Ethernet 2. Here's information about the Ethernet 2 frame. And then when we get to the actual frame here, we've got the, we should be able to see the, where's it at here? Ah, yeah, here's our source and our destination right here. Yeah, so this is the source and destination for our frame. There it is, 48 bits across. And it tells us who it is and what the devices are that are talking, right? Boom. All right, layer 1 does not have a protocol data unit. You simply just encode bits onto a medium. We just launch them over, right? Bits can be sent either in an analog or a digital format. Analog is a perfect continuous wave. This presents problems with noise and amplification. That's true. Digital is a discrete set of steps of data. It is less precise. It's not perfect like analog, but is much easier to filter and strengthen. So I can filter noise out of a digital signal immensely easier than I can out of an analog signal. Now, it's not that we can't filter noise out of an analog signal. It's just analog signals they're a perfect continuous wave. And when things affect that wave, whatever you do to try to smooth it out doesn't, like, think of a piece of paper. You take a piece of paper and crinkle it up. And you could try to get that paper flat again, but it's always going to have those crinkles in it. You're always going to know that somebody crinkled that thing up. An analog wave is very similar to that. All right, we multiplex multiple signals over a single channel. So we multiplex different ways. We use time division multiplexing. We use we use time division. Then we use code division multiplexing, and we do frequency division multiplexing. So typically frequency is the first one we use. Frequency division multiplexing. Then we get into time division multiplexing, and then we do code division multiplexing, and we get more and more dense as we go. So the medium, which is multiple medium is the word media, can be physical or through free space. So physical media can be electrical or optical signals. You got to remember, when you deal with electrical signals, there is always friction, and electrical components, so electrons passing through other electrons, will be affected by the electrons on the other side. Electrons also emit EMI as they travel down a cable, which is electromagnetic interference. So they push outwards from the cable, and other things can also push inward on them and affect them. Optical signals do none of that. Optical signals have very little measurable friction against the photons that go down the core and the cladding of a cable. Fiber optic signals can pass through each other with no complaint. There is no electromagnetic interference, EMI, being pushed out of an optical cable. One of the things I did in college was I built a little tool that I could put over a cable, and I could get all the pulses that went down the cable. Very simple little project you could do. You used to be able to just go in Radio Shack and buy everything. Nowadays, you can just buy it off of Amazon or some of these little places where you get Raspberry Pis. You can get a lot of the components, but super easy to just lay something over the top of a physical cable and get the electronic pulses that go over the cable. I don't know if you guys have ever played with that, but you can do that. It's a fun project. You can do it for under 20 bucks. Well, nowadays probably like 35 or 40 bucks, right? Free space is energy. That's either an electromagnetic or laser waveform. Electromagnetic does not need to be line of sight. Electromagnetic typically travels free space along the ground, or we shoot it up off the atmosphere and bounce it back down, or we break the atmosphere and shoot it up to satellites. All of those things I've done in my career, and all of those things are fun. Laser waveform tends to be infrared or directed laser, and those have to be line of sight almost universally. People might be bouncing lasers off of shit, but I don't really deal. I've never. So you can bounce lasers off of stuff for all kinds of reasons, um, but I haven't. I haven't seen that used for data. I've seen that used for like distance and range finding and stuff. I've seen that for truing up, like how satellites can see the ground with lasers and stuff. But I have never seen lasers bounced off of something for um, data. I'm not saying it can't be done. I'm just saying that I haven't seen that. Typically, our lasers are going to be point to point under 5 kilometers, typically. Because then after that, you start to deal with curvature. All right. Digital to analog, so sample of some wave, and then we start to sample down each of these discrete steps, and each sample results in a binary number that we can then send. And one thing to note is the more, if we were to sample this more and more, then on the far side, when we turn it back to an analog wave, we could be more and more precise. Okay? So, multiplexing principles, it's important to know. When we transmit 2 or more signals simultaneously over a single communication channel, that's typically what we call multiplexing. Multiplexing is an aggregation on one side of a signal. And guess what? If we multiplex on one side, we have to demultiplex on the other side. Oh, wow, look at that. Anything you do on one side of a signal, to make it work on the other side, you have to undo it, right? It's a protocol. Protocol is a set of steps that govern how we do communication. And when we multiplex things, we have to demultiplex them on the other side. That's what it is. All right. Broken down into frequency division multiplexing, time division multiplexing, and then code division multiplexing, or code division multiple access of a system, CDMA, but it comes from code division multiplexing, right? What benefits are there for multiplexing? Telephone systems used to do it. Telemetry, as we push data, satellites, broadcasting, all that kind of stuff. There you go. Secret said, "Sir, you are Saitama." You know, it's funny you say that. I actually have Saitama right there. So when people say, "Why do you do this stuff?" I say, "I'm just a guy who does this stuff for fun." They don't really pay me much around here, guys, if you don't know. But I do this for fun. Well, I get paid a lot as an engineer, but they don't pay me anything here, so not really. But anyways, data communication techniques. Boom. Time division multiplexing looks like this. You've got slots of time that are going to be able to send, and it's interesting. I mean, we could spend hours just talking about the different ways that we have gone about saying, okay, there's this one thing, there's this one resource we have, and we're all sharing it. How are we going to contend for that resource? There are polling methods, polling. I poll and I say, hey, Robodom, do you have anything you want to say? No? Okay. Hey, Secret, do you have anything you want to say? Hey, no? Okay. Hey, Gan, do you have anything you want to say? And I just start asking around the room. And some of you are going to go, well, that's not super efficient, because now it's got to wait. Now I got something I want to say, but Scott already asked me, so now he's already passed on. And, oh, no. Well, then what if I take this polling token that I have and I give it to somebody? So we pass this token, which is how Token Ring used to do it. What if the token gets lost? You know, Robodom's sending stuff and he doesn't pass the token along. He takes the token like to the restroom. It's like the restroom key for the you know, in the gas station or something. He takes it. He doesn't bring it back. He just drives off with it. Well, there we go. Now nobody's got the token, so we got to regenerate the token and start passing around the network again. Make sure that guy. Maybe we start passing over Robodom, because Robodom keeps throwing tokens away, right? There's a lot of this stuff when we talk about a protocol, rules that govern communication. You need to understand that if your system isn't playing by the rules, your system gets kicked. Yeah, if I can't use the bathroom, yeah. Your system gets kicked out, because it's not playing right. We got to go fix you and get you back in line, right? All right. Additional topics. So there's other topics that I added here. There are different types of things. This isn't directly network, but direct attached storage. I've been building direct attached storage directly into some of my clusters, even as recently as today. I have these devices. They exist in a failover state between each other with CoroSync and Pacemaker. And, direct attached storage, one server will have a connection into something. And in this case, we have two. And then high availability, we fail over between the two. So one is the Slurm job scheduler. And then if he goes down, the other one becomes him. Or they can actually stonith each other too. Anybody know what stonith is? STONITH. Somebody go look that one up. That one's a fun one. It used to be Stomith, STOMITH. Yeah, go look it up. It's fun. Then we've got network attached storage. Network attached storage is connected over an Ethernet connection, typically. It could be connected over fiber as well. But it is the same shared connection as all other system traffic. That is in direct contrast to SAN. A storage area network never shares the same traffic at the same connection as a normal network. Now, that is not to say that you can't have fiber channel carved up and then still have dedicated SAN traffic over its own network that is logically on the same cable or something. But the point is they are not sharing the same network, even if it's VLAN assigned differently. All right. NASs tend to be specialized devices running in some type of RAID. RAID is redundant array of independent disks. Used to be inexpensive disks. Then people thought that was cheap. So there's also other high fault tolerant technologies that are out there, but RAID is probably one of the most common ones. You need to know your RAID 1, your RAID 5, your RAID 6. You should probably know RAID 1 plus 0 and RAID 0 plus 1 for however many disks you have. Those are probably the main ones you need to know. And then with your RAID 6, 8 plus 2 is the common government one. So it's RAID 6, 8 plus 2. There you go. We connect via network protocols, NFS for Linux, CIFS or Samba for Windows into Linux shares. And I've shown you guys how that kind of works. Like in my home lab, I have things that are directly connected off of my Linux boxes to Samba. And then I can just, I can just pull up all my ISOs or whatever all at once. All my ISOs in my network are right here. And then this is also shared out via NFS. So it's also over here in my home lab for, let's say I want to take lab 6 and immediately turn him into one of these Kali boxes we keep talking about. And we got a Kali 2023 and we just dropped that DVD in there. And now if we booted him, he would come up as, we're not going to boot him, but we could boot him and bring him up as a Kali Linux box right now, right? Because that's all shared in the network as attached storage. This is an important distinction. Again, if your network file system's over here, so here's your file servers, and over here is your NAS clients, your network, whatever. If your network file's over here, and your NASs are over here, these are network. They're looking at this as a network attached storage. But then these network file servers have a back-end storage themselves. That's your storage area network. That is where block storage directly connects to these devices, typically at bus speeds. When you start putting in hardware bus adapters, and then you have, 200 to 2,000 individual spinning disks back here carved up into what we call LUNs, logical unit numbers, then these devices see them as though they're connected disks. And they're fast, super fast, right? You get a lot of high speed out of these. All right, so storage area networks, again, they're dedicated for passing of data. They tend to be optimized for data transfer. They're going to have your jumbo frames and that kind of stuff. There's no access control lists on them. They just are, you can just connect to them. The devices themselves, so like here's the different stuff I was just talking about. But the way that the devices connect are carved from the storage, and LUNs are presented to the different nodes. They don't see the underlying disks ever. They just see what's presented to them. That's an important concept there. All right. This is a storage area network where you're over here on the Ethernet LAN, and then you got these Ethernet switches connecting to your devices, file servers. But those devices have hardware bus adapters that are connecting them over to these fiber channel switches that are in their storage array. So this is the storage area network over here. and then you are connected and looking at these devices. So to this device over here, this person on the network, these are network attached storage. They're connected to the network. But to them, the back end storage is a storage area network, because no traffic that's going over here also goes and fucking goes to YouTube and looks at cat videos and stuff. None of that happens. That's over this side, right? All right. SANs can also look like this. This is what I was saying, is they don't share the network, but the fiber channel over Ethernet switches can actually carve fiber into individual VLANs on one connection. So these look like they're just redundant switches, but there's actually multiple VLANs here, allowing traffic to go here and here with no conflict. All right. These are other things that are important to know. There's intrusion detection and intrusion prevention systems. Intrusion detection systems just monitor, they don't change things. They look for statistical anomalies, or what we call heuristics. So look, this, easy. Why is this easy? Because I've seen it before. A signature-based detection is, well, we're just looking for something we saw before. We saw some person, we got a picture of some person, you know, that we know is causing trouble, or some packet. This one looks at patterns. This is pattern detection. Statistical anomalies. In the last hour, you know, we've had 1 million web requests. Well, how many do we have in the normal hour? Well, in the normal hour, we have about 1,500. And how many people is that one coming from? Well, that's coming from 5 IP addresses. And these tend to come from about 1,300. Well, we've got a statistical problem there, because that is a wild swing from what we're used to. And that's part of it. It also looks at a thing called heuristics. I'm not going to be able to spell heuristics right. But heuristics are like bot patterns and things that humans do. I could sit here and go like this every 1 second. And to my computer, that did not look like 1,000 milliseconds, 1,000 milliseconds, 1,000 milliseconds. That looked like 980, and then maybe like, you know, 850, and then like 720, because I can't keep a beat for that for crap. And maybe a drummer would be close, but I'll tell you what, a bot will do that at exactly every 1 second. They will send traffic at exactly 5 milliseconds apart. Bots can do things that humans cannot. If you didn't know that your system can do stuff faster than you, let me assure you it can. So these are the things that we look for. Come down here, host intrusion detection. Sometimes we put them directly on the host. Sometimes we put them directly on the network. Sometimes we do port mirroring. So one port takes a copy of traffic and sends it somewhere else. In the cloud space, we call that a gateway load balancer. We send traffic off and evaluate it in real time, right? That kind of stuff. But there's all that. All right. Where do we go from here, guys? So this is one of these things, whenever I get to the end of one of these, I don't want to leave you in a cottywomple. What's a cottywomple? That thing has no idea. It's to travel in a purposeful manner towards a vague destination. It's how a toddler walks. You guys ever seen a toddler just walking out in front of everybody and it has no idea where it's going, but it's doing that in a very purposeful manner? Well, what I don't want you to do is like watch something like this or hang out with us and then not know where to go, not know what to do next. So I have all these other things. And by the way, this is up in the Discord for you guys. But there's kernel stuff you can do, and there's networking stuff you can do, and you can go get into monitoring. And there's a bunch of free hands-on labs out there in Killercoda. Killercoda is free, guys. It's the best price on the web, free. I don't own Killercoda. I don't charge anything for my labs. I couldn't if I wanted to. They don't charge anything for my lab either. Ah, but what does stoneth mean, Doc? We never got to what stoneth means. Stoneth means shoot the other node in the head. It is a way to fence clusters. Yeah, it is a way to say that node is not acting the way it should. I'm going to murk it and keep continuing on with all the load because the other node is not properly sharing out and doing its job. So I'm going to kill it and become the head node. And one of the worst things you can do, and I've had this happen before with luster systems, both of the nodes come up and it's basically see who can kill the other one first. Yeah, that's what stoneth means. Stoneth means shoot the other node in the head. It is a cluster way to kill off other systems from serving out your resources so that only you are king. And I'm telling you, I've seen nodes come up and it was a race to see who could get up first to kill the other one. It's like they were like waking up over and over again, just shooting the other one and then dropping down dead and then getting up and doing it again. Like some weird... God, that would be like some weird, like creepy, like horror movie with cowboys or something. They just keep waking up and shooting each other and falling back down dead. It's basically what was happening in this Stoneth situation I got in once. So anyways, which by the way, if you ever want to know about it, I don't ever let failback occur automatically. Failover can happen automatically. I never allow failback to happen automatically. And you can go look up failover and failback. If you don't know the difference between them, go put that in your search and look up failover versus failback. Yeah, Texan Stan. Yeah, did any of you guys see my my thing in Discord? I had a Discord on it. I posted up in memes and jokes, and I said probably only I'm going to think this is funny, but it was stoneth in theory, stoneth in practice. That's hilarious to me, but it didn't get as much laughs as I thought it would. But you know, all right, let me get that out of the way there. I think Breaking Bad is actually in New Mexico, because I'm from Phoenix, and which is in Arizona, and I'm pretty sure Breaking Bad is in Albuquerque. So, all right, questions, just message me in Discord. I tell you guys all the time, just message me on the actual Discord where everybody can see it. Don't just whisper stuff to me, because I work and I teach, and I'm pretty busy, so it's easier to get a hold of me if you do it out in front of everybody. Because then people are like, oh, hey, I've seen that or whatever. And I tell you guys all the time, this isn't the Scott Show. I got all kinds of other engineers out there that are better than me at this stuff. So I kind of bring them in on everything. So, all right. Guys, I never got to the last thing I was going to do. Or actually, it was the first thing I was going to do. But then I was like, I got to get that networking stuff done. Tomorrow... We're gonna build another lab. It's gonna be one of these security labs. We're gonna make sure that we have it all set up and working, so that we have some more labs to do over the weekend. And then, yeah, we're just gonna keep building through, get more and more labs in here. But I'm gonna try to get a couple more labs out. And then also, I got to get the book updated. I don't know where we got to. Hold on, I know that we had. Let me get down here. Let me see. I thought I did most of these, but let me make sure that we have our syslog in here. Right before the end. Okay, our syslog's in there. Good. Okay. Well, what we'll do then is we'll add it to the book as well, and then I'm gonna probably get that one and one more in, and then we're gonna push the book again. Because I haven't published a version of the book in quite a while, so I want to get a new version of that out to everybody. I don't know if you guys know, but if you use that cool little tool called LeanPub, anybody who's ever bought the book gets all the published updates of it in the future. So I have quite a few people that have picked that up over the last year, and I'd like to get a newer version of it out with more stuff on there. So, and then also, if you guys like the Prologue Labs, there are free labs all over the place. I think we're up to like 60 something labs maybe, I think, on Discord or on Killercoda. So, all right. It's late for me. I'm gonna go pass out. Let's go find somebody to raid on the Twitch side. I can't raid anybody on the YouTube side. I don't even know how that works. But let's go see who I'm following. Oh, Sid is on. We're gonna go hit up Sid. We were talking about him earlier, so we'll go raid over to him. He's probably doing some kind of networking stuff or some kind of audio engineering stuff. So we'll go raid over there. But I appreciate you guys coming by, and I will see most of you tomorrow. I'll be on at least for a little bit of time tomorrow. So I will see you guys then. Take care.